bridge design. Sometimes you might feel that I think for the last 5 sessions, we spent a lot of time to build the foundation. I think today is going to be the last part of that one, the bridge articulation. I think so far you have some the idea about when you are designing a bridge, the people involved in that one, and what are the elements actually in the bridge, and then what sort of criteria you use when you're what sort of engineering principles like serviceability limit state, ultimate limit states, and then the wind and earthquake and other elements, how we're going to get them, this probabilistic approach, not in detail, but you have some idea about that. And then about the bridge loading, I spent 2 sessions because there are quite a the vast area. You just need to understand, because that is the primary load we identify. We use in the bridge design is traffic load, and then what we are using is not the real loads, they are the load models. We went into detail in the Australian standard aspects, but we touch base with the excuse me, what is in Eurocode. So, and then from there we looked at what are the load. For example, the last week we looked at the earthquake, creep, shrinkage, and the collision, and then all those loading. And then we looked at our loading. We separate into 3 elements, what we call the permanent effect, transient effect, and thermal effect. And we saw that these loads, and then we categorize into groups A, B, C, D, E, F, G, H kind of a thing. And then all this loading, we combine them to produce the worst case scenario in the bridge. In addition to that, the load combination, for example, we looked at if there's the earthquake, and then how we're going to combine the earthquake loading with the other bridge loading. And then if there's a bridge built across over if a motorway go across the existing road or another road, so then if there's a crash on the substructure from the vehicle underneath, so then how we're going to look at this design in a special scenarios. And then these are the things we looked at so far. And today I'm going to discuss with you bridge articulation. So the bridges are like us, is moving all the time. I think their movement is not like us, they are not running, but slowly is moving. And then they are long structures, heavy structures, big structures. And then we see how we're going to articulate them. If you could remember the first session, I mentioned to you that what we are talking today is when we looked at the bridge as a whole, we separate the bridge into 2 systems. The system 1 is the superstructure. The one below is including the foundation, we call substructure. And the substructure, superstructure always linked together with what we call the bearing. That's where these 2 elements link together. So we're going to look at how this linking element behave, what sort of function it got, and then what are how we're going to see this one in detail and how to understand them. If you understand this 6 session in a proper way, if you are an engineer with some experience in structural modeling, you should go down and you can start designing bridges, because the bridge modeling and application, bridge design, they are very straightforward thing. And they are not complicated. You can make it complicated, looks complicated, but in terms of principle, they are not, because if you have this basic knowledge, then you can build on that one. Then, as I mentioned to you last week, because the earthquake and wind engineering is one of the key part in bridge design or any structural design. To add to that one, the structural dynamics is one of the key thing. You need to have some elementary understanding about this one when you design, if you are a structural engineer. So as I mentioned last week, I spoke to my professor who taught me the structural dynamics when I was doing my master's back in 1992 to 94. He was happy to deliver a lecture, and he's willing to do that lecture on next week. So next Friday, the lecture topic he will decide this weekend, because I inform him the audience and my intention, what I would like to convey to you all. The earthquake engineering and wind engineering as a whole, if you have anyone been to AIT, everyone knows about this professor. His name is Penan Vanichai. He got his PhD from University of Tokyo. I think he's the compatriot at the same time with I think a professor is in civil engineering faculty in University of Moratuwa. Professor Nanakara, I think they were in the same time together in Tokyo, if I can remember correctly. And he got his Dean from Tokyo, and now is currently the professor in structural engineering field of studies in School of Civil Engineering in AIT. Is actually involved in addition to his teaching and research, the other work, disaster preparedness and mitigation management field of study in AIT. And you can read about him. As far as I knew back then, when I was a student, he laid the foundation to develop the wind code and the earthquake design standard for the Bangkok. I remember before I left Thailand, 2008, that was established and then is in use. Along his 30-year career, he did a lot of research and he did a lot of teaching, and then all the students are master students and PhD students. So you got a really good opportunity to listen to him. And then he's a very practical kind of a professor, because he's actively engaged with the industry as well. And then you can ask a lot of questions. So if you have anything related to your work, not related to bridge, or if you are designing a building, or if you are designing another structure, if you have any concern about this one, you can speak to him, because he got a very good understanding about what is happening in Asia in terms of earthquake and wind engineering. That's the one reason I invited him. He's humble enough to accept my invitation and to deliver this lecture next week. Next Friday, exactly same time, is 2 hours. I will send the proper information with the topic and everything on as soon as I got from professor. And then please let your friends and others to even the students in the universities. Please ask them to listen to this professor. Yeah, it's really good. It's kind of a once in a lifetime opportunity for you to listen to a person with that much of experience and the knowledge in the structural dynamics. So the next week, I'll be in the presentation with you all. I will introduce you to the professor, and then he will continue. Please note that, because the 12 p.m. in Colombo is, I think it's 1:30 in Bangkok. So the lecture will be 1:30 to 3:30, because it's still it's a working time. So sometime he might have his own the appointments after this 2 hours. So then, the lecture will be, including Q&A time, is the 2 hours bit plus. So get everything ready. And if you need to get anything clarified, please don't hesitate to ask the questions. Or even if you are interested to do a master degree or a PhD in AIT, in structural dynamics, it's a good opportunity for you to get to know him. Yeah. All right, then we go to our session today, the session number 6, the bridge articulation. So I'm explaining why do we need that, and then I will explain how we're going to apply this one for the common bridges. And then the bridge articulation, we use the bearing and expansion joint. There's not many, only 2 elements. And then I'm going to explain you the performance of the bridge bearings and the joints, and then the selection of the joint and design lies the bearing replacement and a special consideration. This all basically cover within the lecture, within the other slide itself. Then a Q&A session. And before I start the session, because I'm going to prepare an assignment combining all this last 6 session, and then I will give it to you. So then I want you to answer to those questions and do some calculations. Then only I think you can get a feeling about you can enjoy yourself, plus you can estimate yourself where you in. And then since I'm still will be around for the few sessions, so if you have any questions, you can clarify that one. In addition to that one, in this session, there are so many information you can find. I didn't put everything in the presentation slide. Instead, I copy all of them to in the material. I think the resource, the folder, I think if you go to today's session folder, there are a lot of reference materials I included there. So you can read them. If you have any questions, so you can send me an email. You can ask me. I prefer you to send me an email to my private email address, because sometimes the office email, it won't deliver. Sometimes it's better to send it to my Gmail address. In addition to that, while you are working, if you have any questions related, so please feel free to ask that one from me. If I can help, I will help you. All right, then we begin with today's session, the bridge articulation, the parameters and issues. I asked the question, why do we need bridge articulation? So there are so many pictures on this one. There are so many dot points. And I would like to you to participate with me, because that will help me as well, because frankly speaking, sometimes you may be sitting with your friend next to each other, but or else you are staying at your home in your phone and you are walking around and maybe listening to me, but I'm talking to a computer. So therefore, that's why I would like you to give me some feedback. Yes or no, at least that will be help. All right, then. Why do we need bridge articulation? If I ask that question, so now the answers, the way I thought, there are so many, hundreds of reasons there, but I just put a couple of them in this slide. Okay, bridge are subjected to complex loading system. I think you agreed with me that one, because you saw the last 2 sessions, the bridge loading and the complex loading system, for example, earthquake, wind. So you can't predict that one, even the live load, not the actual one we are designing for, right? We are using models. Those models, the very different from country to country, the design code to design code, they are not the same. So it's subjected to complex loading system, right? And yeah, those loading, especially traffic loading. The traffic loading is a primary loading. Is subjected to traffic loading, is a moving load, is time dependent, is constantly changing. So then our bridge, when is subjected to this heavy load, it will deflect and it will move. So then the bridge structure is constantly is subjected to constant deformation. Like I mentioned, between those link, we are talking about that link, superstructure, substructure link. If a superstructure move, then how is going to affect that one onto the substructure will be decided by this link we call the bridge bearing. So the is subjected to constant loading, is subjected to thermal expansion contraction. Yeah, even you can see it's 24/7. The temperature changes, and then we got the around the clock in the countries like the other part of the world, because like I'm in Sydney, like here, we got 4 seasons in the year. But if you go to like the country like Canada and Europe and some part of the US, they got an extreme weather condition during the seasonal changes. And in addition to that, bridges subjected to creep shrinkage and construction staging. We saw this stuff because the creep shrinkage is happening very slowly over the years. Like in normal term, we talk about the creep of the bridge. We talk about 30 years. It's quite a long time. The construction staging, every bridge you build is different, and then some of the bridges, same bridge, you build in the 2 different places in 2 different ways. The construction staging is complex, and bridges are the long. Sometimes it's 40 meter, 20 meter, 10 meter span, sometimes couple of kilometers in length. So then it's subjected to variable ground conditions. So because of that, is subjected to variable ground condition, then it's subjected to variable deformation. You saw the last time when the differential settlement caused the rotation of the structure. So that's affect the articulation. So bearing expansion joint. And the bridge will be subjected to complex deformations. Yeah, of course, when combine them together, it is complex and subjected to extreme events like earthquake, wind, flood, collision. So you can't quantify them. You just estimate them. You can't quantify them. You saw the last time the couple of structures hit by trucks, for example, the collision. Some of the bridge substructures twisted. So this thing is hard to estimate, but you have to design your bridge for those things. And the bridges are made of long members. Of course, yeah, the bridges are made from like a 5-6 meter long to a couple of kilometers, hundreds of meters in length. Like there are suspension bridges as long as 2 kilometers. So yeah, it's quite long. And the geometries are complex. It's quite obvious. These geometries, they are different to each other. So you can see, I'm not going to explain these pictures because you have seen enough these pictures. I just put them in there for you to get some feeling. For example, this industrial ring road project is the same in the background, the complex geometries. And because these things are moving, right? Moving, so it can't swing like like when you are walking across some of the suspension walkway bridges, you notice you just swing from one end to another. You can't design and build bridges like that. So it's made of different material. You can say it could be steel, it could be concrete, or concrete with different properties. A steel concrete together, and it's got a different element. It's got the girders, it's got a deck, it's got a barriers, and it's got a bearing. So many elements in there. So, and you got the substructures, column, foundations, and then you got behind the bridge, you got abutment, approach slab. All of them are linked together, combine them together like our body ourselves, right? It's made of one piece called bridge. Then when you are designing and when you articulate or detailing, if I may say that, you have to pay a special attention to each and every element, but I describe in this dot point. In addition to that, most of the bridges that you use pre-stressed concrete or the post tension in apart from the steel. I'm not concentrate to the other special kind of bridges we use using polymers. I think I'm focused on the common bridges we are designing a day-by-day basis, and we build them. If not properly articulate, the bridge will be subjected to complex deformations, and it's caused a lot of the forces. It's going to affect the bridge. At the end, what happened? The poor performance, and sometimes you may have to replace the whole bridge. Yeah, because these are there's a couple of the dot points I included here for you to understand why you has to pay so much attention to design this one. I should say this at the very beginning. You can design your substructure and superstructure perfectly okay. But if you haven't designed your bearing, or if you not properly articulate your bridge, is similar to you. We got your hand and everything. One of your ligament is go in one of your joint, then you can see the pain you get. So you can move around your arm and things like that. That is the example I can give it to the terms you can understand. Bridge also exactly the same. So then you need to pay special attention to this one, because if you see in terms of the whole bridge design, construction, and the cost point of view, this the bridge element bearing made from piece of rubber, and the expansion joint made of piece of steel element and a piece of rubber, they are not that expensive compared to the overall cost of this bridge. But to get the correct performances and to get the right design life of the bridge, these elements play extremely vital role. That's very important to know. You need to understand. Yeah, it's very important. So the next slide is this you saw enough. The bridge articulation I put for the sake of making this presentation correct, subjected to the bridges, subjected to your bearing expansion joint, subjected to complex loading system. You saw this one: permanent, transient, and thermal, and construction loading, of course. Construction load also play a significant role in the articulation design. It can be you can use the permanent bearing or temporary bearing during bridge construction. I will give you some example later on. Because the reason the loading system, because the behavior of the bridge, as I mentioned, is mainly is the bridge bearing and expansion joint, no articulation, play a vital role. So then you see our load based on the models. All our load is based on the model except the dead load. And all of them are tide dependent. It could be traffic or it could be creep shrinkage. And the withstand extreme loading, wind, the earthquake, thermal, and all this loading, you just predict based on the model and the probabilistic approach and the flood and everything. So it's subjected to those loading. Then you have to design your system to absorb that one. So then the bridges is subjected to complex bridge articulation. So it's not easy for me to find the pictures or something, because bridges are long structures. Even if you see a bridge is really deflect, you can't see from that your naked eye. So rather I draw pictures. Yeah, the first one, as I mentioned, most of the members, we use the pre-stressed concrete. So you pre-tension the girder. When you pre-tension the girder, this girder will create a camber. So from the fabrication yard itself, you get a deformation in the structure. Your bridge is camber like that. It's a time-dependent thing because it's related to crepe shrinkage. And some of the bridges, I didn't draw this one, we construct with a sack. For example, segmental box girder bridges. Because when you apply we do opposite. Because the pre-tension girder, we pre-stress press and cast the girder, release it, and it's create the camber. This one, we get this pieces of concrete segments and assemble together, hang them from the gantry, and we post tension. Yeah, similar to pre-tension in the bottom phase, we apply that one. If it is a simply supported girder, so that post tension, the post tension will push the girder up to get then it will create the sack. It will create a hog, sorry. Because of that, you have to build your bridge initially with a sack. So it's not only you get a camber, the hog, you get a sack as well in your design. So this is very initial stage. So you get the bridge during erection. You see the bridges normally erect. You hang from inside. They are the lifting point. They are not exactly the same as the support point. So it will deflect, and you place that one on the temporary or permanent supports. It will deflect. It will deflect due to its self-weight. It will deflect due to when you're casting the deck. It will deflect when you're casting your barrier, your surface bearing course, or the asphalt, or when you are building the drainage all sort of loading when you just keep adding. In addition to that, these loads are kind of a permanent load. Your traffic load, you just keep moving, vary with the time, subjected to that. In addition to that, creep, shrinkage, and the time dependent one, that create because it's a pre-tension, post-tension, the elements, they will be subjected to this changing stress regime. Because of that, your deflection will be vary. So the deflection will be a change, mean the bridge will be rotate. So the girder will be rotate. So when it's rotate, so that's going to affect your bearing. So because it's attached to that one. In addition to that, your support will be settled, because the differential settlement in the foundation, because I think if you speak to your friends in the geotechnical team, they will explain it to you, because like we talk about concrete and a steel, concrete got a creep, shrink, the soil will do the same thing. And then because of the different ground condition, ground profile, you get a differential settlement. You notice that one. It could be this loading, the foundation can be go down. In addition to that, you will see in the next example, some bridges we calculate with the upper camber. So the settlement, the settlement it doesn't want to be go down in all the way down. It could be go up as well. So it's complex. We don't know exactly what is happening, but you have to do the model. You need to have a better, you need to guess, estimate, and you need to predict these thing, and then you need to assemble them together. In addition to that, okay, the longitudinal movement in the bridge is happening all the time because of the vehicles is moving. It's not the rotation of the girder itself. If it is a brake or thermal expansion, contraction, creep, shrinkage, this create this girder in longitudinally is moving in and out all the time. In addition to that, the bridges are built with the complex system. You got a super elevation, you got the geometries, and when you put the loading, you can see this. I put that one in the box girder, the loading on the one side. You loaded one side, heavy truck. So then you got a twist on your cross section, and because the load transfer across the bridge cross section, that twist will rotate your whole bridge and the whole system. That will induce another system of deformation onto your bridge superstructure. So you can see, and if you combine them together, in addition to that, there will be another, the mode of the forces and deformation will be acting onto your bridge. All those things, when you add them together, so you got a complex deformation system in your bridge. So then the element is going to link in the top and bottom, has to play a vital role to understand this and transfer that one cross and accommodate that one. I should use the word accommodate that deformation and make sure that any of these deformation is not going to have the significant bad impact on the bridge, so the bridge can perform. So it's very important for you to understand. Please don't make things very complicated. Make simple. I think most of you play with jigsaws now. You know, if you want to assemble that one, it's maybe a small puzzle. So if you just need to assemble your pieces together in a proper way. If you miss one, it's going to affect. Similar to this, just understand in a basic way. Okay, we load this, it will deflect. This is the way. This is how it's going to happen, because it's involved construction, staging, and this thing. This is what's going to happen to my bridge member. So then that's going to impact on my bridge bearing. So please think in that way, in a simple way. Don't make it is a continuous, is this, is that. No, not like that. Very simple way to understand that. And then we combine them together, then you will have a feeling what is I'm getting out of my models is right or wrong. Because the bridge modeling, you got thousands of members sometimes, thousands of load cases coming out. So if you do not have a basic the picture about what you expect from this model, you will get confused. Then, if not bridge properly articulate, yeah, of course, you know the things is happening. I put this crash one. If you not properly articulate, in the sense, if you not properly restrain this bridge, you can see it's not properly designed substructure as well. Yeah. And then you can see this flood loading, the bridge pier tilt, and it's not properly articulated. It's superstructure, substructure link. There's a failure in here. Even we do all those things, but you can see when they were building it, it's a very, the construction, you can see the people think bridge bearing is a piece of rubber. You just need to put that one on top of the substructure, then you can place your superstructure or bridge girder on the top. That's it. That is rubber. It can deform. It will do the job. So that's really wrong, right? So you can see these pictures will have different meanings. It's all fail. And the one is, we call the bearing is walking. Is, you see the bridge is full, the whole system, the out. And then they try to jack the bridge and try to place the bearing in the position. So what happens if bridges are not properly articulated? Because bridge is subject to complex loading, it will cause the bridge members to failure. The members, it could be a whole bridge. Sometimes it not fail, but it crack, it deform. For example, if your expansion joint pop out, so you can't drive your car because your tire will jam with the expansion joint, especially the finger plate joint. It's come out. You give the punch in your tire, so it's not serviceable. It's a hazard, traffic hazard. So in addition to that, if your bridge not properly articulate, if there is a defects in the bridge, bridge is subjected to it's got a massive dynamic effect that amplify the bridge behavior, that amplify the static load you assume in the design. It's going to reduce the design life of the bridge, and it's a hazard to it's a risk to the road users. And then it generates sometimes noises, especially the expansion joint. At the end, it's increased the cost for the maintenance. Increase the maintenance cost when increase the cost for the road agencies. At the end, the road agencies is maintained by us, so by the government from the taxpayers' money. So then that's burden is coming back to you. Because of that, it's quite important to understand these aspects and to do the right design. Please note that I think the amount of money we spend for the bridge articulation, it's compared to the overall cost of the bridge construction, and it's quite small. Because of that, I think if you are a bridge engineer, if you are a supervision engineer, you must be very strict. And you said there is no compromise in this one. You had to go back and design what the designer asks you to do, because if you compromise this, you compromise a lot. So it's not going to, and another thing, please remember this one, you are supporting bridge on a bearing. I think only the bridge inspectors, they go and inspect the bridge bearing, no one else. So you don't know until, because they not go and inspect the bridge each and every day, morning, evening, and afternoon. They visit them, the bridges, like a 2 weeks, 3 weeks, 4 weeks time. So then months time, then everything has happened. So because of that, during that period, nobody knows something happened to the bridge. You will see that one, if there's a crack or if there's a tilt or something, then you can complain. So that time is already failed. So because of that, you need to keep that one in your, if you are designing the bridge bearing. And even you need to explain to the contractors, even to the other engineers, the construction engineers, how important that one. It's not just to place this and grout that one and place it. It's a piece of rubber, it's heavy. The bridge deck design enough reinforcement, strong enough. No, it's not going to work that way. So then I just put this on the procedure for you to, when you are designing it, is a very standard one. To understand the behavior of bridge element is very important. Each and every element, you will see at the end of this presentation, why did I put? Because it's not the bearing and expansion joint, it's a main thing in this one, but the small element, other elements in the one is very important. And when we had to, of course, we are structural engineers, we always do analysis. We have to analyze and we have to design. When you do the analysis and design, so you have to select the type of the joints and the bearing. This is the vice versa. And then you have to detail and you have to properly document your assumptions. So one way, because you design, someone else build, someone third party is going to maintain. So you need to communicate that one to the people they're going to maintain in the future, what your assumptions are, what is your thinking. So that is what we develop drawings and report. So you need to build up them. Another is very importantly, you need to understand the construction aspects of this one, because you can't leave the construction of the girder and the deck and the thing to the big boys, the contractors. But when you are designing the bearing, this is the smallest element in the bridge. You're going to place it. It's play an important role. You need to have a very good understanding how they're going to build. Whatever the detail I'm going to propose is possible for them to build. Yeah, and in addition to that, the road agencies and the designer itself need to write a proper specification, proper methodologies, quality assurance and quality control system. You did all those things. If you not properly maintain, if you not look after your bridge, the reason is we are designing bridges for model loading, right? So it's subjected to very different kind of loading. So nobody can control the overweight trucks on bridges. I think because of that, you need to maintain that one. You need to understand what is when you maintain, if there's any movement in the bridge or anything, you just need to make sure that you capture that one. So these are the basic procedure. I think is applicable to every element you design in any structure. So this is, I just put in here to emphasize how important this the bearing and expansion joint design, or to articulate in the bridge in a proper way. Then the next couple of slides, I'm going to discuss about the how we're going to articulate the common bridge types, right? This the one simplest example is when you are construct a flyover bridge, or if you just build a single span bridge across a flyover bridge, it's got a multiple span, but they're simply supported. And then if you get a bridge over creek or a small road, you can have a single span or multiple span, but you got expansion joint either end. And then what you do, when you put the expansion joint is, as I mentioned many times, you create a gap between the bridge elements, so it will allow the bridge structure to freely move in and out. So this is the quite common and simplest form of the articulation system. We use the expansion joints and bearing, and it could be in every span, or it could be you can have a multiple span with the link slab. I think I had discussed this one, the multiple span and the link slab. One example, I think in the session 2 with you. Then you can have that one. So you can see this picture in here. I got across the bridge abutment. The bridge abutment is sitting on the pile, or we got a curtain wall, we got a backfill behind, we got an approach slab, and then we got your bridge superstructure, and superstructure is supported on bearing, and the bearing could be manifold. You will learn later. And then we have the gap. That gap between two bridges, we provide the expansion joint. So then, when the bridge is moving in and out, and then we allow the bridge to the bearing and the expansion joint to facilitate that one. Suppose you design a bridge, you calculate the gap you need for a creep, shrinkage, thermal contraction, expansion, those things, and the earthquake and wind and the breaking load, that's required. Let's say this gap is 50 mm, right? For some reason, somebody builds this one with the 30 mm, right? So what are you going to do with that? Are you going to leave that bridge with the 30, or are you going to do something else to, because you know that your bridge is going to move 50 mm. So actual construction is 30 mm. So it doesn't matter, there is a gap, it's okay. Yeah, the only thing what happen if a bridge is moved back, it will go and engage with the curtain wall in here. Are you going to leave like that or not? Someone can answer me. Are you going to leave that, or are you going to do some remedial measures to that? In the construction, during construction, there will be a lot of what we call non-conformances in the construction. We call NCRs, and they raise what you're going to do as a designer, right? Yeah, you can say you have to come up with the solution to make sure that the bridge is not go and engage with the curtain wall. You need to protect that. Yeah, because the 30 and 50 has 20 mm different. I mean, you don't want to worry that it's 20 millimeter. You see this length of this bridge. It's not going to happen that way. So you can't leave it that way, because another thing, sometimes you might say, we have a lot of heavy assumption in the braking and other load. Is never going to happen. This is just a small cars use this bridge. Because of that, we don't want to do anything. So you should not have that concept. You must go and fix it. Yeah. And this bridges, when we were using in here, as I mentioned, the most common type bridges. We use a simple construction, I-beam, super T's, plank. Yeah, it could be concrete or steel and concrete. The bridges could be simply supported. With the link slab, you can get your expansion joint length to a further apart, and the bridge movement accommodated by joints. The longitudinal loads are and the vertical loads actually together taken by the bearings, and it could accommodate the differential settlement, and it's less load on substructure. Is it clear to you? Because these bridges, mostly with simple bridges, we supported on elastomeric bearing, the piece of rubber in here. So the forces transfer across this one. Yeah, because of it's allowed the deformation in the structure, the less load will be transferred to the substructure. This form of construction is very easy to build, and we call this one a kind of a, not the right technical term, is a floating bridge. It's just allowed to float, move in and out. And this form of bridges with the link slab, you can go up to maximum, I should suggest, up to 250 meters in length. The bridges supported on the simple support span with the continuous deck. The expansion joint spacing you can increase as far as 250 with a simple bearing. And then it could be increased up to 300 plus even if you want, but you need to make sure the special joints and special bearing and that sort of thing is kind of a specialist kind of a work. If someone is interested to work on that one, can let me know. I will explain it to you. Another thing, I put a note in here, you will see later. If the bridge is longer, expansion and contraction in the bridge will be longer. So the longer the bridge, that's factor will be getting higher, and then that parameter is getting bigger. Because of that, your movement restriction, like if you use a very standard simple type, the expansion joint type we call strip seal joint type, that's accommodate it's about 85 to 125 millimeter. If you go beyond that one, so you need to jump, you need to change your joint type and things. Yeah. And I put this one in big. The deformation of the bridges is mainly caused by creep, shrinkage, thermal expansion, contraction, baking, substructure deformation, earth pressure, etc. Because the reason I put the earth pressure, because this earth pressure depend on the substructure stiffness, is going to rotate the bridge abutment structure that will push your curtain wall. Like when you do analysis, you will find sometime like a 3-4 millimeter in order, normal bridge. But if you are working on a flexible ground, it could be much higher. And the special attention you need to pay attention on earthquake and flood loading. The reason I put the word floating, the bridge is floating, is if it is the earthquake, for example, is subjected to significantly large load. If a bridge is moved, depend on the inertia, it will push in and out. This is many engineers, they don't get it, because sometimes if bridge deform or is slip from a bearing, it cannot take it back because you miss the point. It's very different. Because of that, during an earthquake, I suggest we call you can put earthquake buffer kind of a detail in a bridge with a long span. Like if you have a bridge with the maximum length of the distance between the expansion joint in order of 200 plus meters, it's better to have some small rubber element in here that makes sure that if there is an earthquake, before this expansion joint is jamming before the bridge go and engage with this rubber element, because rather than concrete to concrete, it will prevent the expansion joint is jamming. Another thing, it controls the deformation of the bridge, the longitudinal deformation of the bridge, that sort of thing. But that earthquake load is going to push the soil behind the bridge abutment. I think it can carry a significant passive resistance, because the bridge abutment, this depth at least 2-3 meters. So because of that, I think this is the good prevention measure, because this sometimes the people argue in theoretical point of view. So many equations, so many numbers. It's not that. You need to look at the overall, the global picture, what is happening if this one move and if not come back. Because if the earthquake is the inertia, is moving in and out, so the bearing will provide sufficient dam to bring this one in and out. If this fellow is the move and heat and jam here, it cannot pull back. Even if pull back, it will pull back everything together. So then that create the lot of cracks and a lot of issues with the bridge. So this sort of bridge, because when we were designed simple form, simply supported mean every girder, as you can see in the cross section, whether it's a plank or super T or I or steel, whatever it is, every girder you need to have a support. You need to have one bearing in every end. So every girder you got a two bearing. So you assume you are building a 10 kilometer long bridge. You got a 3-lane or 2-lane on one side. You got a 6 girders. The span is standard 30 meter. Like let's say we put a right number like a 33 meter, 100 meter. You got a 3 span. So every 100 meter, so you got a 6 into 3 into 2, 36 bearings. So you can imagine if you build a couple of kilometer long a bridge using that element, how many bearings you need to replace, right? You need to go and check and keep record. So you need to replace this bearing. We see later, normally the design life of this elastomeric bearing is around 35 years. So then you have to replace this one quite frequently. Another thing, this is quite common. I think you might experience this one. If you not properly detail your expansion joint, during the rain, the water will go across the joint and it's go across your bearing and it's come down, because even you can't stand underneath the bridge. And that create a lot of issues, especially the traffic going around the bridge, especially if you are building this one in a city. Like for example, you can see this picture in this steel bridge. People are driving quite close. And then the higher impact on the joint, because if it is deformed, for example, in the joint here, I think you heard this one I'm telling, and you experience yourself when you are driving over a flyover, the bang noise. always you have, or else if you are driving on top of an old bridge. So even the finger plate kind of expansion joiner, still you heard that bang noise. That noise will generate more impact load on your bridge. And the sometimes it's noticed if you build the bridges mostly with eye girders, with the long span, with the wider spacing, engineers try to do, they use mathematical aspects, bridge design sometime. They said because that now quotes have given, for example, I could remember when I was using Astro, when I was designing the effective width of the bridge, and is equal to the 12 times the thickness of the slab. I think that create the one aspect for us to decide the spacing of our girders. The current standards, you got two small box girders in each end. You put your slab about 6 meters, you model and you work everything. But this kind of a bridge will cause a lot of other problems during its service, the vibration, but those aspects you can't model or you can't check in your design. So especially the eye girder bridges with the long span with a lot of post tension to get the design to work, or the pretension, beg your pardon, pretension, get that one to work, because you got a lot of pretension on the girder because your weight of the deck and this barrier and things. Sometimes the barrier load might concentrate to the exterior girder, cause the bridge to go upward camber. This we notice in some of the bridges, and because of that, if you get upward camber in the bridge, the first thing you can see your barrier got a cracks along that one. You can easily notice. Another thing, while you are driving on the bridge, if it's a long, if it's a not the cup, like a bridge, not a flyover bridge. If it is like expressway, you can notice that one. So you need to pay a bit of attention about the bridge deformation when you are designing this one. I just put this thing. This is a very common type of bridge. This easy to build in terms of the construction cost. I think I explained this one at the very beginning. This is one of the cheapest form of bridge construction. You can find the simple span, simply supported girder bridges with the expansion joint at the end. Easy to build in terms of the cost also is quite cheap, because the bridge construction, if it is easy to build, that means it's cheap. If it is difficult to build, so many stages, it's complicated, the construction costs skyrocketed. Yeah. Any questions up to here? Any questions?
Hello, Mr. Rohita.
Yeah.
You hear me?
Yes.
Mr. Rohita, I have a simple question.
Yeah.
That when we model this type of bridges, we usually use pin and roller support for the bridges. So how we can achieve the restraints for floating bridges when we are modeling?
I think, yeah, because I'm going to discuss this one in the next session, the bridge modeling, the special attention I'm going to pay how to model the bearing. Yeah. And how you can model there are empirical approach, but this modeling is based on the design standard parameters using that one, because for example, you will learn in the next session, but anyway, I will explain it to you. Like you will learn more information during the next couple of slides. The bridge, the bearing is a piece of rubber. It's going to, when you apply a load vertically and horizontally, the vertical load is the reaction, and the horizontal load is the whatever braking and all this loading, creep, shrinkage, thermal, those loading acting on the bearing. So got a horizontal load, got a shear deformation. So we combine these two together, we can model our bearing using like a beam element. Yeah, then we can represent the bearing as a beam element. We can calculate the stiffness of this, because you need to put the right stiffness to get the right behavior of that element. So then you can, for example, your superstructure, you model as a line element. So your column, you model as a vertical element, a vertical beam element, your cross beam, horizontal beam element. So then wherever you have your girder, you can connect using a small beam element bearing. That element properties, I will teach you how to calculate. And if you use like a software like Midas, I think the other softwares is built in there now. You can specify your type of the bearing, the size of the bearing, then it will automatically calculate. Yeah. Did I answer, give you some idea about that?
Yes, thank you very much, Mr. Weber.
All right, then I'll jump into the next slide. This is the one of the common type of, we call semi-integral bridge. This one, a lot of push to use this bridge. I designed and built this one. Yeah, few of them. And I looked at the, a lot of research has done regarding this bridge. I think a lot of push to use this bridge. The main reason is you can remove the expansion joint. The semi-integral in the sense, what you do, your bridge deck and your curtain wall, abutment curtain wall, you link together. Semi in the sense, it's not rigidly connected. It let that one to float, it let that one to rotate, let that one to move, right? And between the bridge, previous slide, you can see the clear gap. I mentioned this gap could be even 150 millimeter or 30, 40 millimeter or 10, 15 millimeter. But in this scenario, this gap is, you can control. This gap is the, whatever the gap you get between your approach slab and the bridge deck. So the semi-integral in the sense, this bridge superstructure, substructure is still separate, but the slab and the cross beam on the bearing location is connected with the bridge abutment or curtain using a dowel. That dowel will allow your bridge to do certain movement, a bit, very bit. Yeah, we call this one semi-integral. The concept developed, I think, in mostly in Europe, especially in UK. They basically developed the design procedure, and I read there are a lot of research, a lot of research, and a lot of engineers looked at this one in detail, how to achieve this one. The simple, the answer is because the people try to take advantage in this form of bridge. The semi-integral side is not fully integral. It transfers certain load. It allows a minor bit of the deformation in the structure. They take the advantage of this backfill behind in here. Sorry, I forgot to mark this one. You know, when you have a soil backfill in here, because if you not do anything, this backfill will push the bridge. The passive pressure push the bridge. It will generate the force. But when you are moving the bridge, for example, the braking or temperature, the expansion, like I show in this bridge, the bridge try to push the substructure, the abutment try to push the soil, the backfill behind. So when it's try to push the backfill behind, it will generate the passive, it will generate a passive soil resistance in here. This thing you can say is generate passive soil, but there is a relationship to generate the passive soil, to increase, to get the maximum value like K0, for example, to 3. You need to have a considerable deformation in your bridge to deform this fellow to a certain extent. Yeah, that deflection to be significant enough to develop enough passive resistance in the back. Your bridge need to bend in opposite direction, right? To bend the bridge, you need to have a flexible foundation. So there are so many parameters. The good example, we can use this one with the bridges we build with the reinforced soil wall, because we isolate the bridge, the pile like couple of meters with that one. The same principle I think they use in the design, especially in US, not now, maybe 20, 30 years ago. And if I just explain it to you, the principle, I think mainly in Europe, they use the thermal behavior of the structure to the thermal deformation of the bridge utilized to push that one. Another thing, when you apply a braking load on the bridge, right? If you connect this substructure, superstructure together using this dowel, then that load will be transferred through the curtain wall or through the bridge abutment to your soil, because then you're braking in here B, push against this abutment, the backfill there, that generate the soil pressure. This is the ideology, this is the principle, right? So the one thing you can realize, it's not like in the normal bridges. In the previous bridge, you see we didn't have a dowel in here. If you put this dowel, that generate a significant load, because this load, let's say, is for the sake of calculating number, this number is 600 kilonewton, the braking load. Oh, no, for 200 kilonewton, right? So then you need to put the braking load 200 kilonewton, enough number of dowel. The dowel with shear force is more than 200 kilonewton. Your dowel shear resistance has to be more than 200 to transfer this braking B into this, transfer that one to the curtain wall. If you can do that one, then you can push that one across. Another way, you can come up with the different mode of solution, different detailing thing to transfer that one load, not from the top on the bottom as well. In another places in the girder. So when you apply this load, the bridge will be applying that load, the braking load, back onto the abutment. So that create the bridge additional bending and the forces in the pile. The pile has to be bent, pile has to be flexible. Because of that, the people mostly use, if it is a small span bridges, sometimes people tend to prefer to use this solution. It's no harm using that solution, but please note that you can't just go and use it like, okay, I just want to use the semi-integral bridges. That code describe the procedure. It's not going to work that way. You need to have a better understanding, especially the flexibility of the foundation. The other thing, this one, the single span or short length, the small skew angle, you can design with that. And the supported on the bearing still, because the bearing will be subjected to lesser, smaller shear deformation, and it will be subjected to vertical load. It doesn't matter. Then your bearing dimensions, like a height, you can reduce a bit, and you can remove the expansion joint. And yeah, you can remove the expansion joint. I put here the suitable for bridges subjected to significant temperature changes. I just put this one. I think this one, you get this temperature changes mostly in European countries and other part. And I really don't think, like, especially like even in Australia or even in Sri Lanka, you won't get the significant temperature changes to make that one. And the substructure and superstructure connected by a dowel in here. You need to have a special detailing at the end to make sure that because your approach slab has to be supported. Normally, approach slab is sitting on the curtain wall. Now, what you do, you try to extend this your bridge deck on top of the curtain wall and connect it to that one. Then you have to create a special detail to support your approach slab. And the thermal expansion will resist by the passive resistance in the bridge, because when thermal expansion is try to push. I just want to put this one in here, because when the bridge you build after that, because of the creep shrinkage, the bridge length always shorten, right? Because sometimes there is a point that you can see your creep and shrinkage is large enough that your thermal expansion isn't going to do much, right? Even if you design your bridge assuming thermal expansion is going to get carried by the passive resistance back in here because it's pushing against the backfill. So it's not going to happen that one. After maybe 3-4 years later, you will notice that your creep and shrinkage calculation is larger than your thermal expansion, and there is a gap always in the bridge. So whatever the backfill pressure in here, it could be K0 or Ka. The K0 or Ka, it may not go to Kp. So then you won't get that advantage. If you are using, if you are designing these bridges, don't blindly analyze and get these numbers. Please see the time frame and see these numbers and check before you get into your analysis, check that one first, because if you know the length of the bridge, if you know the property of the girder, you can easily calculate that grip shrinkage, or else still you can estimate that one properly. And I put here, the behavior depends on the flexibility of substructure and temperature variation. Applicable places with considerable temperature ranges and lots of research done, as I mentioned. No significant benefit for construction cost and performances. This bridge is very expensive to build. You trust me, this dowels and this complicated detail in here is quite expensive to build. Sometimes you have to spend a lot of money compared to your saving the expansion joint. Performance-wide expansion joint may be good, but if you properly build, you don't have any issues. Another thing, please remember that the design life of the bridge is 100 years, right? So if you want to replace this bearing, the design life of the bridge is 100 years, the design life of the bearing is 35 years. If you want to replace this bridge, so you have to jack the bridge up, right? You need to make sure that this connection is able to jack the bridge. If your deformation, the flexible substructure deform more, rotate this thing more, then you can't jack this bridge, because when you're jacking the bridge, this area will crack. This is one of the key problem in these bridges. When the people build in the theoretical basis, and then at the end when they want to repair it. But if you are building this bridge with, you will see later with the strip bearing, no problem at all, because if you build the bridges with the strip bearing, you can achieve 100-year design life. Because of that, there is no bearing replacement. So then it's good. So keep those things in the mind when you are designing it. And I put this one in here, the special attention you need to pay: flexibility, foundation flexibility, ground settlement. If you flexible ground, but if you get a rotation in your substructure in here, especially in the approach slab, it will pull your bridge. I noticed there were issues, and that create this double, because it's linked with your bridge deck. If it is a bend, that create a lot of issues in your bridge. Yeah, I noticed this one, it's cracked, and the aspects in that one, because the design life of this dowel need to be made of a stainless steel if you want to build this bridge, if you want to achieve the 100-year design life. I said the dowel should be stainless steel. If you use the stainless steel dowel, the yield strength of the stainless steel is quite low, like Fy is 205 compared to the Fy of reinforcement. Or if you go to bolt, you can go grade 8.8 even. They are much higher compared to the stainless steel. So your dowel size is larger and you need more. And you need I put the issues: design assumptions, bearing replacement, settlement, and construction. Any questions? No? Is it clear or it's not clear? Shall I ask a question from you guys? So they like, if we are going into so much trouble, so why do we need to build this one anyway in the first place? Yeah. You can't rule out that one that way. Like, as I mentioned, if you design your bridge with like a simple span, if it is sitting on the, you will see later on strip bearing, you don't have a bearing replacement. If you properly design, detail, and build this one, I think it's good, because you got a smooth riding surface all over the place, because your bridge is free of maintenance for 100 years. Yeah, yeah. But when you design and detail, you just need to pay. You have to pay a lot of thing you need to detail and understand, analyze, and clear. I have this element in here in this picture, 3-span bridge. This is sitting on the bearing, and you can see with the link slab is connected at the end and is designed as a semi-integral. You can see this dowel detail is dowel is diameter. This is the real detail, the one bridge I designed. The diameter of the dowel is 40 millimeter. You can see the I think I mentioned somewhere here in the FY is 205. And you can use for bridges with link slab. Please note that if a bridge length is total length of the bridge is longer than 70 meter, it's not recommended. You can use this one for with a sharp curve. You know that because it's sitting on this small detail with the small tolerances in here. If it is a curve, lateral forces, because if it is a curve bridge, even the temperature or the creep shrinkage that affect. In addition to that, the braking and the centrifugal force create a lot of complex deformation on the bridge deck. It can't accommodate because the 750 diameter, the radius is, the bridge is more or less a straight. And then like if you get the 750 chord versus 70 meter in length, you can see that the delta value, the chord distance will be very small. And then your skew angle is matter. You can't use this solution with the quite sharp skew angle. You know that if the skew angle is significant, that will generate different forces in your dowel. Because if this dowel is exceed the force, it will bend, right? If this one push more, it will bend. So that cause, if this dowel bend and jam, so the bridge won't behave the way you want. You don't want to jam many dowels, you just do one or two, then it's gradually adding up to the other one like a domino effect. Like I mentioned, if someone interested, I think I just need to find all this, my papers. It's back a long time ago. I read this stuff almost 10 plus years ago. Some bridges they tried with in the local areas using a steel piles with the casings in here to make it more flexible. I said the bridge has to be flexible, and they put the steel we call king post I sections, and the weak axis in the longitudinal direction, not the strong axis, the weak axis, to make it more flexible and increase the unbraced length of the pile, adding the casing in there. So that way the bridge is the flexible, it can push in and out easily. So you can come up with this solution, by the construction cost and the risk you associated with the performance is quite high. Yeah, that was those papers they discussed, and the case studies they looked at. Yeah, and I'm not discouraging you to not to use it, but you can use it, but with a lot of care. That's what I want to say. And any question in this slide? Okay. All right, then I want to say one thing to all of you, because now every time when I ask no question, there are two things I can conclude. One thing, yeah, all of you is very smart, everything you understood. The second thing is, yeah, you won't get anything. So we can see where you're standing, where your position between these two extreme men when I give you the assignment, right? So you may need me to, for example, explain me how you're going to design and build a semi-integral bridge. I will give you the location, these are the places I want to build this bridge. You want me to give me the reason if yes or no, why you not going to use it, or why are you going to use it? Okay, then I can test you. All right. Any questions again? No. Then I will jump into fully integral bridge. This picture is not so nice. Yeah. Fully integral bridge is there are so many varieties. I think I should have put that picture. Actually, I forgot. we use the fully integral bridge in Makasan Bridge, I could remember. But maybe I will put that particular bridge in our in the resource presentation folder. The Makasan Bridge actually geometry looks complex like this. Yeah, not exactly like that, but quite complex geometry we got. We use, when I was in Bangkok, we use fully integral bridge. There are many forms in the fully integral bridge, but if someone is interested, please let me know. I can give you drawing. I can explain it to you, or else I can put them in the resource folder. You can see how they detail and build. Fully integral in the sense because if you're going to talk about fully integral bridge later, this one I'm talking about simple form. You have a simple span, or I'm talking about girder type of a bridge, or super T kind of a bridge. You have a couple of span, like with the link slab. So you want to make it fully integral. So you connect your curtain wall and your deck together. Yeah. I do not recommend you to design this one without bearings. Yeah, if you are designing, at least you had to use the strip bearing or pad bearing to support the bridge, to make sure there's some small flexibility. What's happening when you fully integral this bridge, right? When you fully integral bridge, imagine the way we build. First thing, imagine we talk about creep shrinkage. Imagine this picture, you got a thermal, expansion, contraction. I forgot to put the creep shrinkage. You can add that one yourself. And the breaking load. You build the column, you build this headstock, the abutment headstock, and then the curtain wall. Place the bearing, you place your girder, and then you can do a construction staging. You can decide, you can cast your deck with the construction joint, and then you can link these two together. So when you are linking these two together, you can just use the reinforcement coming out from the curtain wall and the deck reinforcement. You can link together as like making L bar in here, U bar in there, U bar in there. You put the two reinforcement there. You create a beam kind of element at the end to make these two elements linked together, right? So that create your fully integral bridge. So what happened when you finish the fully integral bridge? So after you finish your construction, creep shrinkage start happening in the bridge, right? There is a differential shrinkage between the deck and the girder, and the creep and shrinkage as a composite section. When it's happening in here, this whole thing try to push towards it, yeah, contract in the bridge. When it's contracting the bridge, this try to bend to the front like that, right? You got a face, you got here tension in this face. Your structure try to bend that way, right? So when the thermal expansion is happening, the bridges try to push in the other way, right? When there's a breaking is happening, the bridge try to deflect like a frame, like in one way, right? So all those things happening in the bridge. I should have to have a lot of line element diagram for you to understand. I thought you get that one, because when you put this bridge into perspective like a one frame element, when you apply this load, the bridge behavior different. The behavior depend on so many parameters, not the single parameter. Because of that, is fully integral. All these forces generate if it's a floating, this breaking will translate into a deformation. That deformation will translate into a shear force in the bearing that will transfer to the substructure. But now it won't happen like that. This whole breaking force will absorb by the whole bridge. That bridge, if you model this one as a frame, portal frame. So that portal frame will deflect that, will create bending, deformation, right? So then that create a very complex loading system on your structure. Another thing we know, the creep shrinkage is time dependent. That's what I said. The way you build your the day you cast your girder, you build your bridge section of your slab in here, you do this linking element later on to make sure that the creep shrinkage effect on this bridge will be you make it smaller, right? You can do all this. The design is time dependent. You need to have a proper plan about the construction. You need to have a proper assumption. You need to lay down. If this one significantly deviate in the construction side, that's going to have sometime the effect. Another issue I'm finding in this bridge, you don't know where you find this crack in this bridge, because if the forces, it's not the way if you design this one, if bridge is not going to perform the way you assume during the design, especially in this back face of this column or in here, if you get a crack in your this construction joint or in the back face of your abutment or curtain wall, you can't see them, then there will be a significant durability issue, because in here you got a water and the backfill in here. That create a lot of issues in here. You can use this designs, but when you were using it, right, it's not like people say you can remove your expansion joint, therefore we're going to use it. Yeah, don't look at that way, because you need to look at the bridge. As I mentioned at the beginning, the expansion joint and the bearing is the least expensive element in the bridge when you are building a bridge. And the performance-wise, you can come up with the better detail, and you will understand if you use the expansion joint to get the performance, right? But in here, if you just to make it in the sake of removing that, and I want to use it, if someone force you to do it, it's not going to work that way. Saying that, you can use this kind of a bridge, fully integral bridge, but I'm talking about the simple kind of a bridge. It's not the complicated one. You're going to look at them later, right? You're going to remove your expansion joint at the end. This bridge, you can design and you can build that one, but you need to pay a lot of attention. It's better, even if you design in your design report or your design drawing, you lay down your assumptions, right? The contractor to see in the future, the maintenance crew, those who are going to say this one, because if there's an issue and someone is going to analyze in 30 years later this bridge, they know your assumption. They with that one, they can understand where's the problem is going to happen, what is the problem, how are we going to fix that one. Yeah. So I just have a couple of notes in here. I think it's not semi-integral. It's wrong. You need to change to fully integral bridges. Single span or short span, small skew. No expansion joint. Significant large stress induced due to creep shrinkage, thermal effect and breaking. You can see that one. And the foundation flexibility, ground settlement is going to affect, because if now ground settle, that differential settlement affect, because it's a portal frame, I should say. It's a portal frame now with the slender substructure with a very big superstructure on the top, the higher stiffness on the top compared to the substructure. Issues your design assumption, the bearing replacement is not the right word in here. I think if you design this one with, again, I said you can design this bridge with the strip bearing, definitely. And then I don't think bearing replacement is there won't be an issue. You can strike that one out. The settlement, construction staging, cracking and durability, of course, is one of the concern. Yeah. Yeah, you can use this one with the bridges with link slab as well. Yeah, because this one you need to do analysis and understand yourself. These are the type of bridges used, I should say 15, 20 years back, or even before. This kind of bridge the designers tend to use in different aspects, different reasons. But now, because it's the complexity involved with the construction staging and the time, and because the time in the construction is a massive cost in the bridge engineering. Because of that, I think the designers and contractors, they are not preferred this kind of solutions. And even the client, I think they think sometimes it's a massive risk for them in terms of maintenance and the performance aspects of the bridge. Saying that, I'm not telling you that you just don't want to look at this bridge design, but of course you can see the options, but you can see as options, but you need to see all the pros and cons, and then the positives and negatives, and compare that one, and make a decision, what we call the value engineering, or value for money for the project. Value for money in the sense, it's not the initial cost of the bridge, it's the overall cost of the bridge, including the maintenance cost. Any questions up to here? Okay. Then I'm going to go to a different form of bridge. This is also quite common. This we use for the long expressways, we call viaduct. Yeah. You know, the big viaduct, big expressways, they tend to build using box girders. Yeah. One thing is you use a single massive cell. If you're a 3-lane bridge, I think you should have to have a better understanding about this one, because in the reference document section, I put this segmental box girder, the bridge manual. In that manual, if you go to the back of that manual, a different number of lanes, different length, they give you what is the form of your box, dimension of your box. So a lot of information in there. The single box, you can span quite a long span, because segmental box girder, even if it's 60 meters, no problem, you can span them. Therefore, if you build long span bridges, this is quite common. And again, this form of bridge, you can build with many different forms. You will see later. The first one is a single, simply supported, simple span bridges. They place one after another and put expansion joint, or you can create even the link slab in there, and you get your bridge. So you can see in this picture, you can see this the line in here that on the middle of the pier. The span is about 40 meters, and the single cell box, and is supported on 4 bearing. The simple way, like before in the question mentioned, fix and roller kind of a support you can use when you are articulating or supporting this bridge. So normally these bridges we can support with elastomeric bearing, but this very rarely we do. Normally these bridges, the cell dead weight is very heavy, long span, heavy box girders, heavy concrete sections. Because of that, you need to use the pot bearings. So when we articulate the free, this is the symbols we use in the pot bearing. The free end, that means it's free to move in any direction. The longitudinal or lateral, sorry, I forgot to put the arrow, you can put yourself. Longitudinal, the arrow in both direction. Creep, shrinkage, thermal expansion, contract, and go in and out in the same time because of the lateral loading. Example, get the wind loading. The wind loading is in the lateral direction, is push the bridge on lateral direction. So one side you can make it free, another side you can make it fixed. But when you're using the fixed, the bearing, you can got many types. You can see this arrow I put in here. That arrow, the arrow always show the direction it can move in and out. So that means it's free to move in the lateral direction, this particular bearing, but it allowed to move in the fix in the longitudinal direction. So longitudinal direction is fixed. It's not move in the longitudinal direction, but it can move in the lateral direction. So the other one is the red dot, that is a fixed bearing, fully fixed bearing. that prevent movement in any of these directions. So this is a very standard form of the articulation of this bridge. But if you need, you can articulate in different way. You can let the bridge to move in the longitudinal direction. This one this kind of articulation we use in a special locations like this picture shown you in here. We just build the box girder bridges. This bridge is about 52 meters in length across the as a highway, and then this bridge only is a single span bridge. So as I mentioned before, we utilize the curtain wall and the passive resistance behind if a bridge is moving across, and we restrain the bridge movement, providing some restraint system in the bridge abutment. With that, we allow the bridge to move in the longitudinal direction. When we, I just need to mention, when we check the longitudinal deformation in the bridge are significantly small compared to the bridges like a 200, 300 meters in length. So this is the common type of the bridge articulation system in the this viaduct kind of a construction. Simple span construction is the one in the top. Yeah, this the one in the top. So when you are building these bridges, you will see later, these pot bearing are very big. You have to build in a special way. Most of these bridges we construct using gantries. You saw before. Then these bridges can be supported on temporary bearing or jacks or some other form. This kind of arrangement is common in the segmental box girder viaduct construction. So because of the heavy reactions, we use the pot bearing. Special attention you need to pay how you're going to replace the bearing. And sometimes you can design with 4 bearing. You need to have a 4 bearing because every pier support 2 end of the girders. So you need 4 bearing. So if you see on the one pier, it's a mirror image of that one. One pier you got 3 fixed, and the bearing I call with this symbol in here, we call guided bearing. Guided, all combination you have in one pier. This is one of the common form of articulation we provided in this form of bridges. And the analysis is also important because all the time when you design and build this kind of a bridges, as I mentioned, we provide the sag on the bridge for segmental box girder bridge to get create the sag at the beginning. Then when you post tension, the bridge will be go to the upward deflection. So then you get the right bridge profile. You need to do the construction staging, creep shrinkage, thermal braking, and earthquake analysis are critical. I just want to go back to this picture on the bottom. You can, as I mentioned, this is the guided bearing. This bearing, one direction it can allow to move, but the other direction it is fixed. So why did I fix this bearing, this bridge, particular bridge in that direction? The reason is the earthquake load. Yeah, because if you put everything free in this bridge, because this heavy, these girders are heavy, they are massive concrete elements and they are quite wide as well. If I let that the horizontal earthquake force, the bridge will be dislodged because it will just simply move. Yeah, because as I mentioned, the earthquake is the inertia force. There is nothing in there to push this one back. So because of that, we restrain this bridge in that direction. Yeah, that's the reason. Yeah, otherwise you will ask, I think I maybe forget to rotate this one in the other direction, like in here. Yeah, because the bridges are expanding and contracting in the longitudinal direction, but it's still Rohita restrain the bridge on the opposite direction, the lateral direction. Why do you want to do that one? Yeah, so the reason is the lateral load, mainly the earthquake load. Any question? No? Okay. This one. It's the same bridge, segmental box girder construction. You have seen this one enough, this picture. The same bridge, but is a different. What is the difference between this one and that one? This one, the segmental box girder bridge construction, span by span, but it's simply supported, simple supported girders, right? Simple analysis, WL squared by 8. But this one is different. This one, you can see these slender girders. You can see on top of this bridge pier. If you go here, you can see how wide this column in here in the substructure to accommodate two bearings on the pier. If I give you the numbers, the spacing between this bearing in the longitudinal direction is 2 meters. Is the width of the bridge. On that longitudinal direction, the column dimension is 2 plus 750, 750, 350. Yeah, but this bridge is very different. It's quite thinner. The thickness is as small as 800 mm or 1 meter. You can see in here, the difference in the construction in here is a segmental box girder bridge. When we are building it, this bridge we design as a continuous span bridge. Yeah. This is not a long viaduct. This bridge is just like a overpass kind of a bridge. This bridge, even you can build like a viaduct like this, it's no problem. And but you have to have expansion joint at a certain distance. So the difference between these two structures, the deck is continuous. The construction is in very different way. I'm not going to go in detail there. And the construction is very different, the way we build these bridges. And when you analyze this one, you analyze this one as a continuous beam because it's very easy. Not like I-girder bridges, it's a box girder bridges. You can represent your box like a line element. So then it's a one line in here is doing simply supported. If we go back to the basics, like the normally bridges we span in the more or less equal span. If it is the load is W, for example, dead load, then the bending you get the maximum is WL squared by 10. The design is not that difficult, easy. But the complexity involved in this one here, the continuous span bridge, you got a sack, you got a hawk. We are designing this one with the post tension. You could see from this picture a lot of post tensioning happening on the top pin. You can see all these box out on the top here. You need to have the post tension on the top as well as the bottom. They compare to this bridge, the simple construction, you got only the sagging bending. You only need to have a post tension on the bottom. So this one, you can achieve a lot. The example in here, you can see you need every girder 4 bearing that you can design this one with the 2 bearing, right? So you can reduce the number of bearing. And because you are designing this one as a continuous span, you can reduce the amount of the post tension, for example, required in the bridge, but it's a very complex. The construction is quite complex, and it's take time, and then the analysis and everything complex. I would like to make a point that one because sometimes you think I achieve a bit of a post tension in here, I reduce this one a bit, I reduce the bearing in here, but with the construction staging involved in this one, sometimes the construction of this kind of a bridge may be expensive than the construction of a simple span bridge when you come to the viaduct construction. Yeah, it's a very, very different aspects in the design. I can't tell you which one is cheaper, which one is better, but the performance-wise, if I say in terms of the rideability wise, the continuous bridges of course are good if you put the expansion joint far away. So you can come up with the same solution, the simple span in this box girder, but with the link slab solution, you need to go bit. You have to do a bit extra work, then it would be better. In terms of sometime the construction cost, because I don't have a answer to that one, but yeah. When you speak to contractors, you can get some input from them. But this kind of a construction will be carried out by the specialist contractors. You can't find everywhere this kind of a contractor, especially if you want to buy these gantries, you have to hire them. Because of that, the solution is not copy and paste, but you need to have a lot of thinking before that. So we go back to the this slide again. The bridge is supported on the bearing. You can see every pier you got a 2 bearing. You can make this the bearing as the free bearing. The free bearing in the sense it's it can move in any direction, or else you can have a guided free, or you can have it fixed in this articulation solution, one on the top and one on the bottom. Both can be used. If you use this, the one on the top, this you can apply to only for the bridge like a certain length. It's not like a viaduct kind of a solution, because if it is a viaduct, the deformation you have to double, because it's continue on to the other segment as well. So in that situation, you need to use the one on the bottom. And the one you can see in this drawing, you can't use it for the bridge with the sharp curves. Yeah, you can use, but not recommended. Then you have to go to the one on the second is better. Again, you can see the bridge can move in the longitudinal direction and lateral direction. Is happening all the time. And then we have this guided bearing. What we call is allow the movement in the longitudinal direction, but I have is fixed on lateral direction to make sure that during an earthquake, the bridge is not going to slip away from the deck, because it's not easy the bridge to fail in the longitudinal direction. Only thing it will happen, it will jam against the abutment curtain wall. But in the lateral direction, if you do not have a restraint, the bridge will slip. Yeah, it will rotate then. So yeah, if you go to segmental box girder solutions, either one of these is quite common. I think if you construct long viaduct, I think the some designers it's sometimes the designer's preference. If you work like what we call the design and contract kind of a construction, I think is the combination between both the designer and contractor. Then the contractor will dictate what sort of design solution I need to build this one. They know from their experience which one is going to cheap in this particular environment. So that's sort of the thing they will consider, because this construction cost of this bridge, they are significantly large compared to girder construction. So the bridges look pleasing and durable, and the less maintenance and so many lot of advantage for the client. Yeah, sometimes when you compare the overall cost for a long wire, for example, like expressway kind of a construction, sometimes this design solution overall for value for money is maybe better. Yeah, and this particular solution quite common in Bangkok actually, used with the flexible substructures. As I mentioned in here, depend on the flexibility of substructure, the expansion joint length, we can extend up to kind of a 300 meters in length. Heavy reaction, of course, heavy loads, you need pot bearing. Special attention, because if you design this one without longitudinal restraint, some bridges we use the special devices we call lockup devices or attenuators. You will see in the next slide, we can use them, and or else you can replace with the fixed bearing. This fixed bearing, even you can put that one in the middle of the bridge. You don't want to put that one at the end. You can decide this one. When we were doing the analysis, some designers prefer to put that one in the middle. Why? Because this is what we call the temperature point, where the creep, shrinkage, and everything is going to be zero at this point. The contraction and expansion is happening toward in and out from this point. So then they prefer to have a fixed joint at the middle. Then the analysis involved, of course, the construction staging, these bridges, the creep shrinkage, thermal breaking, because the centrifugal force, of course, and the earthquake is very critical. You need to pay a special attention when you were the designing the bearing. Any questions?
Hi, Rohit. It's Sean.
Yeah. Yes, Sean.
This guided bearing, for example, if we allow to move in a longitudinal way, and then we use lateral restraint blocks, right? Normally, for the
put this kind of a bridge, we can't build lateral restraint block, chance, because these boxes we can't build. It's coming
so
like
what
a
are the
segment.
procedure? Yeah, what is the procedure to provide that guided bearing in longitudinally and laterally? What methods they use?
You mean
what type of methods they use to, restrain the lateral movements and the
if you restrain the lateral movement, for example, in this case, what we need to calculate, there are two bearing in these corners. It will take all the lateral load. For example, wind. Let's say the wind pressure is 3 kPa. The depth of the bridge is 3.3. Then when we figure out the line load is 10 kilonewton per meter, the bridge's span is, let's say, 40 meters. Then 10 times 40 is 400 kilonewton. This 400 kilonewton minimum wind load has to be absorbed by these two. Let's say equally distributed, 200 kilonewton. It's a different when you do earthquake analysis. Yeah. If a ground acceleration with KP factor, when you put that one, if it is a 10%, if a 13% of the 13% of the gravitational load in the lateral direction, because of this mass, that will generate significantly large forces in here. The addition to that, I will explain this one later with the bearing. When we go to discuss bearing, these pot bearing allows certain kind of a slight movement in the rotations. That's the advantage having this bearing. So that will have a bit of a flexibility. But when we were, I think if I answer your question directly, like I mentioned, earthquake and wind, we calculate the lateral load. Even if there's a centrifugal, we can calculate the lateral load on each of these bearing. Then we asked the bearing designer to design this bearing for that load. Yeah, I think I have some drawings I put in the today presentation folder. You all can see the guided bearing detail. A lot of detail in there. These shop drawings actually I put for you to read it. If it is not there, I will include a couple of those drawings. You all to see the actual detail of these bearings. Any more questions?
Yeah, that's all good. Thank you. For the fixed bearing, we mostly use the pot bearing, right, to get that reaction.
The guided also, these are the pot bearings. All are pot bearings.
All are pot bearing. Okay.
Yeah, yep. Segmental box girder construction, you will see the is a preferred one is a pot bearing, because the contractors hardly use elastomeric bearing. I think we design single span voided slab and box girder bridges with elastomeric bearing, but of course not the viaduct type of construction. Yeah, it's mostly pot bearing. Yeah.
Okay, thank you very much.
Any questions?
Hello, sir, I'm Diane here.
Yeah, Diane.
Yeah, I'm assuming these continuous span box girders are in situ cast, or can they be precast construction as well?
This is a precast construction. We call this segmental box girder. You will see the cast in situ one in the next slide. This is a segmental box girder. The bridges, I think even you can see from this gantry, they are coming pieces by pieces. I think I have some slide in the previous example. The segmental box, this bridge, the deck, we cut it into slice and we assemble, and then we post tension and together. Yeah, these are precast segments we fabricate in the site, and assembled together in the at the construction site using these gantries. Yeah, the next slide you will see the cast in situ post-tension box girder bridges.
Okay, so there is no difference between construction. There is no difference in construction time between continuous span and the segmental box girders.
No, the okay. The bridge is made from segmental box girder in the sense, let's say this length of this bridge is 400 meters,
Okay.
right? 1, 2, 3, 4, not 400, 200 meters, right? The span is 50 meters, right? Span is 50 meters. So then I want to build this bridge, 200 meters and the 50 meter span bridge made from box girder. Then what I'm going to do during construction, I will slice this single span, the 50 meter length, into 20 segments. So then one segment of the bridge is 2.5 meters. So then I got 80 segments. I split this bridge into 80 segments. You can see one of these box section in here. All these pieces we fabricate in the yard, bring to the site. So there are pieces, then you can place along the bridge length. You will see the bridge on the ground. So then you need to assemble that one on the top of the pier. So we use this gantry and lift that one, and then using the post tension and the there's some methodology is on the post tension. We use the what we call the PT bars, and we use the mono jacks and then push them together. We put the epoxy on this face, and we have a shear key on there, and then we assemble them together, tied them together, and then post tension and make the bridge a continuous span in the side. Yeah, that's what we do. Is it clear?
Yeah, it's clear. Thank you very much.
The next one is the yeah, of course, the this Panankawa bridge. This photo you have seen before. This gantry. Yeah, I love that one. It's 1,800 ton gantry. You use in this bridge. The color red is my previous company, Unique Engineering color. You can see all this board and even the barriers we color from that. It's all the same red and white color. Oh, it's all right. We go back to this, and then the continuous continuous span box girder bridges integral with substructure superstructure. I mentioned to you, I discussed this bridge before in the session too. Why we did this one. You can see this this width of this deck, if you could remember, 27.6 meter. Depth of the structure is 2.5 meter. The span between this the piers is 48.5. And in this bridge, in this bridge, what we're going to do, sorry, this bridge, we do cast in situ construction, Yeah, it's different to the previous one. Previous one, we get the segment and assemble together, but this kind of a bridge, 27.6 meters width, it's not that easy for you to lift with the gantry to build that one, with that this sort of environment. But I should say, I think the people already built even the larger boxes in a 50 kilometer long the Banatrat Expressway in Bangkok using segmental box girder. Yeah, of course, can build. Yeah, if you just Google and see the Banatrat Expressway, you can see the special form that we get the designers and the contractor get the columns and everything shaped to make sure that that construction is possible. We put that one apart. And this the continuous span segmental box girder bridges. I'm sorry, I forgot to show the construction joint in this one. The location of the construction joint, it's in between in here. I think I can draw this one if I, okay, anyway. We have if I say this from the center of this girder, like a 12 meters away, 0.2, if I could remember the number, 0.2 times the distance, we have a construction joint everywhere. That's where we build the span. You can see in this the picture on the bottom right-hand corner, I have the first segment construction I've drawn in here. Okay, the continuous span bridge. This, after you finish this bridge, it is continuous. The superstructure and substructure is integral together. Then when you apply the load, creep, shrinkage, thermal expansion, contraction, braking, all this load apply on this bridge, it will be applying same like a portal frame. Yeah, the portal frame in here, the cross girder, you replace with the 3D, this box girder you replace with the line beam. It's on the top superstructure. And this column you replace with the vertical beam element. And then because I just draw the footing, yeah, because there's no footing actually in this particular bridge. So this one you can represent as a transverse beam. You have 2 piles in here. You can replace these 2 piles as a 2 vertical beam, and your soil pile interaction you can replace with the column. That's where you develop your portal frame. In this particular beam, when you apply the load, the whole bridge will be tend to move in and out. Whole bridge push in and out, push in and out. And with the flexibility in the structure, we can push the expansion joint length quite significantly. Yeah, that provide the rideable surface. I just want to mention to you that the number of expansion joint length you can decide based on the total length of the bridge. Yeah, that's one thing you need to remember, the total length of the bridge when you split into segment, because you can't have a 2.5 meter segment like it will be 3, 4, 5 segment in whole segment in the bridge. That's where we're going to have expansion joint. You can make a decision like that. So you can push this one as far as the possible using the flexibility of the structure. And then of course, this one you need foot bearing at the end, but you don't have any bearing at all in this one. It's a bearing-less kind of a bridge. Yeah, so less maintenance. Of course, the analysis construction staging is very important because you are building span by span. You cast one span, you put the other span, and you keep going on like that. You can see in this particular bridge, to launch the gantry, we have to build the column head first on the bridge. This section of the bridge you have to build first. The reason is because you don't have this picture. Maybe I will put in the later on, if someone is quite keen to see how they're going to build this one, the way the pictures with the bogie on this column, and then the way the launch nose is reaching the bogie. And then we can have this bogies in here. Because of that, to have the bogies in here, you need to have a column head. So that is how we're going to build this one. The important thing, this bridge, you see you can have a many span, but you have only 4 bearing at the ends. So this bearing, it doesn't carry much reactions in here, especially because it's a continuous span bridge. And then when bridge is deflect, it's move. Yeah, as deflect, it's going to move, but most of the forces, the load will taken by the design is similar if you just design the frame with the continuous frame with the column in here, even in the building or anything, is quite similar to that one. But need to remember, because these structures the subjected to creep, shrinkage, thermal, that loading generate a lot of the additional loading in the system. In addition to that, you can see I have these dot points in here. 1, 2, 3. They're in different locations. The first one, between the pile and this headstock. The way this element link, the pile is linking with this footing, right? Because I said this bridge built with two piles. I think you saw this one. I saw in a previous example in the presentation. You have 2 piles. And here I have this point in here. And then the column, connection between the column and the footing. Then the connection between the column and the box girder. I mentioned in here, these are the plastic hinges. When these bridges subjected to earthquake loading, and these points generate massive movement, and these points generate significant bending, and that could close the plastic hinges. If you go to earthquake designs and if you look at the literature, look at the photos, you can see at these locations, you got issues. Why we got issues at these locations? Can someone explain me why? Sometimes we got the issues in the middle of the bridge as well. So why we got issues mainly at this location, you saw most of the time. The one reason you can see when you build the pile first, you got a starter bar here, you link that one with your footing. The column is orientated in the vertical direction, your footing is going in the transverse direction, right? It's horizontal. People not pay much attention. You bring your spiral because you have to stop here. Then your other structure is coming. You say you got your starter bar in there. But you need to make sure that this continuity you maintain. You make sure that your construction will allow to form a plastic hinge in here. Yeah, it can generate extra confinement in here. Similar to this one. When we are building a column, you not build everything together because they are staging this construction joint here. So you just put the starter bar in here. This is one of the weakest point here, here, here. It's the same. You stop the construction of the column here, then you build your box girder, the headstock or box girder in here. So then your starter bar, continuity of the starter bar and the confinement you need to create in here. I didn't worry about this one on the top of the girder because the girder is the post tension, right? This bridge has got a lot of ductility. In the same way, if you not properly detail, yeah, this bridges is heavy and ductile is a big frame. It can absorb a lot of inertia, the big earthquake force that cause a lot of problem. I just want you to go to, you Google it. You can see the lot of bridges, the way it's failed, where you got your starter bar in here, the other starter bar in there, and you don't have a proper confinement in here. Yeah, it's gone. Yeah, because of that. That's what I mentioned during the earthquake, the design discussion. The earthquake design, even if you miss something, it's okay as long as if you properly detail that one. If you properly detail your stirrups, your starter bars, your confinement reinforcement, if you properly detail, so then you can achieve a lot of things. This thing you will learn when we were designing that one. That's the reason I put this one in here. In terms of the bridge articulation, this is quite easy. The bridge is continuous. You have expansion joint at the expansion joint and the bearing at the end. This bearing, because the bridges are still heavy, you can use the pre-bearing if you like to, because the movement of the bridge is quite significant. If you use the pre-bearing in here, you need to make sure you need to provide the lockup device or another form of devices to make sure that the expansion joint is not going to jam. You will see that one in the next slide. The other thing in here in this bottom of this picture I mentioned, because during construction of these bridges, we can put this one on the jack or temporary pier. This special temporary bearing we call the sandbox. This is quite common and quite cheap element to be used. The way I don't have actually a picture. I didn't have a time to draw that one. This is like a, we had a steel box like bottom plate and then the box in here, the vertical faces like in the thickness in the book, right? We fill that one with the sand. And then we have a small pipe there. I will tell you why we need to have a pipe in on the bottom. We fill that one with the sand and we put a steel plate on the top, and then we load the bearing. We use that one as a bearing. Because if you put the bridge on the temporary bearing, because after construction, you need to remove that one. You have to transfer your load from the bridge to the permanent bearing, right? To the permanent bearing. So then if you use the sand boxes, how can you do that one? Because your height, if you use the jack, you can you can change the height of this the bridge. You can lift the bridge, and then you can place insert your bearing, and then you can release the jack. Then the load will transfer to the new bearing. The principle we use in here, we build the sand jacks because they are very cheap, very cheap. I think we build this one a little higher, and then we build on that one. Then we place the sand jack in the different locations. Anyway, temporary bearing, you have to place not in the different location, like in here, for example, compared to the permanent bearing. After that, you bring the permanent bearing, you install and everything, right? You grout on the top, you leave a little gap, and then, so when you want to transfer the load, if you finish grouting and you let the bearing grout to harden, so what you're going to do, because I said we have a pipe on the bottom, right? In that pipe, actually, we seal that one. We remove the seal and we flush the water inside. So when you flush the water inside, what happened? That sand will come out, then that steel plate will go down. So you create the gap, you take that one out, but there is no support in there. So then your load will transfer to the permanent bearing. This is the very, one of the chief form of temporary jacks that people use in this kind of a construction. Nothing wrong with that one. You will see the same principle we use in the design of the bearing. We use the same principle. Yeah. To explain it to you, I have the maximum axial compressive values, permissible values for bearing. I included in this presentation slides for you to have it. This is the idea we use, like a triaxial test you learn when you are doing the study the soil mechanics, because of the confinement, because you have a steel plate around, because when you push the sand, you got a vertical compression there. That vertical compression push the sand, because there is a confinement, you can have a significantly large pressure in there. So because of that, it's not going to fail. Yeah, this is that's what I put in here for this temporary bearing. We use sand boxes. I think if you are a construction engineer, sometime you may come across this one. Yeah, this is quite common in the construction industry, because some contractors, they don't allow, some countries, they don't allow because of the safety reasons. But I didn't see using a jack and using a sandbox, temporary jacks and sandbox doesn't make much difference. Yeah. And any questions? Okay. Then the other form of the bridge is the same kind of a bridge. You can see the continuous span box girder bridge in here. We've got another continuous span box girder bridge in here. But the difference in both of this is this particular one is the single the single cell box, but the width of this box is the width of this roadway is only 10.6, the width of this box, compared to the previous one 27.6, and we got a slender column. And then this bridge got a complex geometry, and to articulate this bridge, we sit this bridge is like before, is sitting, we got a continuous span, you don't need bearing, it's integral, substructure, superstructure, or the column and the box girder, but you got a bearing at the end. We use single spherical bearing at the end. The main purpose of this spherical bearing is like it can rotate in any direction. Yeah, it can rotate in any direction. A spherical bearing, in the sense you got the convex and concave system, right? And you got your steel, you make a concave and put the convex, and you put the in between Teflon. That's why it's allowed to rotate. So this bearing is spherical. Because of that, it can deflect in any direction. That deflection will allow bridge to move freely, right? But it will rotate it will control the movement in the longitudinal direction at this point. But we need to remember the girder get the depth. This particular structure, the depth of the girder is 3.3, and that a small rotation even on the bottom will create the significantly large deformation on the top. Because of that, this particular construction, we use what we call the lockup device. This, you can see one of the picture in here. Here. This is an element, like I will read what is in there. Basically, it's like a fluid and not like a fluid damper. Like lockup, this not dissipate the energy quickly. It's effectively act as a dynamic brace because it will link these two elements together. When you, for example, the braking and the seismic and the wind and all these things, this hold this structure together. And then the dynamically is act together, and then slowly it will release, because this thing we make sure that this bridge, some bridges when designed special conditions, we have this situation. It's very different in here. You don't need that sort of environment in this bridge. In this bridge, you can build with because it's a straight line bridge. You don't worry about anything. You can use the like in here. At the end, you can use the fix and the guided bearing to hold the movement of the structure, one side, and other side, you let that one to free to move. Then with this thing, you can control the deformation of the structure. But in here, you don't have a choice because of the geometry of this. You can see one expansion joint at this location, other one is inside underneath this this diagram in here. Yeah, it's about 600 meters in length in here. Is go on a spiral curve. Yeah, this solution will let the bridge to free to do his own stuff, but it's controlled from here. It's not going to go beyond that one. Yeah, it's hold up together, right? If bridge tend to move beyond that point, right, this will hold up together. So then you need to, when we were, for example, in the modeling, if you want to link this two together, you can replace the lockup device as a spring, and you can see the stiffness of the spring. You can evaluate based on your deformation and the force requirement, and then you can design that one. It's not that difficult to attach this one. You can see this, the one end. Other thing you have here, the lockup device element you bring here, and you put a pin and fix it. This force, the axial will be transferred, that one across to the shear to this base plate. This base plate will be transferred, that one across to this girder using the bolt we included in here as a shear. So these are the kind of a special arrangement we use in the bridge design, because I just put this stuff for you just for your interest. But if you design bridges over the years, when you get sometime you get an opportunity to come across this kind of a design and construction of this kind of a special bridges. I think in especially like if you are young, not like us in your generation, I think when you come to our age, this kind of a bridges will be not like one stage, multiple layers of bridges will be quite common in every city in the world. The way the world is changing now, the cities are changing. So you may need to have a multiple layers of this kind of interchange, go one on top of each other to cater the traffic and to get the human from point A to B. This is this code of construction. So after you get a couple of years of experience, you get a chance to design and build them. Yeah. Any question in this slide? Nope. So then the other one, the balance cantilever bridge. The balance cantilever bridge in the articulation, I just want to say, because it's quite obvious, the way it's built like the cantilever structure. You can see we build the pile, putting column, and then we start building this progressively increase in the length of the bridge. The column, the one picture you are seeing in the bottom, this we use for about 70-meter span bridge across the intersection. This is the Panankawa Bridge. This 227-29 meter in length, one of the largest span bridges. You can see this keep building construction is in progress. What I try to point out in here, this bridge, of course, in the two end, you got a bearing. You can have a form of bearing, whatever the way you like. But the few things I just want to point out in here, you can see this diagram I have drawn, the blue line A, and then the bridge beam I represent using the red line, and the B I again put another dotted line in upward camber, and then a column I put show in this diagram as a dot point. So the A, when we were designing this bridge, because this is a cantilever, we know cantilever structures is always deflect. If we put the load P in here, the deflection is PL cube over 3 EI. Very simple to calculate that one. So we post tension on the top, put the compression in here, that will again push the bridge going upward direction. So that everything goes, the bridge is going up. So then the weight of the bridge will push this one down. So then when you are building this bridge, you have to put the camber in upward direction. So this is, you have to estimate. That's why I mentioned last time, when you are calculating the creep and shrinkage, it's very important, right? So you put the upward deflection and you calculate. Another thing, as you can see this one, these bridges are very steep. These bridges are very steep. It's never behave, trust me, never behave like your computer model. It's behave very differently in the site. Still, the people, there are not many people build about 20, 30 of bridges in their life. Yeah, you can't find them that much. Yeah, this bridges sometimes is like building tunnels, very rare. So still people go in the theoretical approach. You calculate the camber design, you get your best camber curve. It's the best you can get, the best analysis you could do, you get that. And every time you build this bridge, I forgot to put some dot point, this red line we place in this blue line, this red line we place in this blue line, right? Then we expect at the end of the construction, when we finish, this point A is going to be on point B, or this blue line is going to coincide with a red line. It won't happen that way. So normally, it's going to happen in here. This bridge will be end up in point B. In point B. Because of that, in the segmental box girder construction, if you build your bridge like just go and straight away, you want to support this bridge in the expansion joint, the bearing in here, you might see you won't get any positive reaction. Your bridge is not going to touch the bearing because it's a very steep cantilever that stay as it is. If you build the bridge, if you detail this bridge like that, it will be there will be a lot of issues. The same issue you are having with this one, with the construction of cable stay bridges. When you are building cable stay bridges, design and construction, they are a bit secret, and people think they are very proud and they design and build this thing. But principle exactly the same. There is no different building a cable stay bridge and this balance cantilever bridge. Exactly the same way we do. Only different is we got a one vertical column on the top and we put the stay cable to reduce the section of this element. That's what we do. But we have the same problem. When we are going to do the cable stay bridge, you can see it's a cantilever element. It's go to other end, do two cantilever segment, come together and we put a stitch for. If the one end, it has to go and touch the abutment. The advantage in the cable stay bridge, because we work with the post tension, the contractors and the designers, they do the stressing level, they reduce at some point, and then they will or even if they stress to the certain point, If you not get the positive reaction, they release the cable stress a bit, let the bridge to deflect and touch. You don't have that luck with the balanced cantilever bridge. But I'm telling, the scale of the bridge doesn't matter. It could be a 50-meter long balanced cantilever bridge. This problem is there. Some instances you haven't seen, because if you are an experienced construction engineer, sometimes if you build this one, you may have this experience, because if this one is not go and touch this, the maroon part in here, I just put, if you use this one as a balanced cantilever, sometimes it's not go and touch, what they do, they put weight in here. They let the creep shrinkage to increase the deflection of the bridge, put some permanent loading in here, let that one to deflect to get the positive reaction. If you can't get that, only way you can get that one is to tension this one using the PT bars. That's never recommended, because the bridge is subjected to dynamic load. If you put the PT bar, it doesn't have much ductility, it will snap out. I think you saw the, when I talk about, in my previous presentation, I show you one, the ball snap out because of the fatigue failure during our fatigue discussion. So it will happen to this bridge. But to get the positive reaction, some designers, they design and they do this one. But instead, now there is a trend now. They do, in this section of this bridge, you build as a cast in situ. The construction is not that easy. It's not the preferred version of the contractors. They don't like it, because you need to do a lot of different way of, because when you do a balanced cantilever bridge post tensioning, you post tension this deck on the top to the cantilever. But when you build this bridge, it's not balanced cantilever itself. It's a bridge with the, if you, let's say you got only two spans in either side, then you got a middle span, then you got a support and either abutment. So because of that, then it's behave like a continuous span. So then the modeling and the different, and you need to have some bottom post tension in here. The construction is a bit difficult, yeah, but you can avoid that negative reaction. This is the, I involved with this bridge construction. I know A to Z about this thing. I've been monitoring this bridge up to certain extent. I work with this. We calculate these camber curves and we monitor this one. We build this one. We know that this bridge behavior exactly to the point. And because the only thing we couldn't convince our client client and others IC to accept, it's not going to behave like that, but you have to build. But the outcome is they're not touching. So you have to create the different way to make it touch to get these the positive reactions right. So that's the reason I put this the segmental box girder, balanced cantilever bridge. The slides in here. It's nothing to do much to do with the bridge bearing type, because this bearing, the balance, these are monster concrete section. You're not going to use the balanced cantilever bridge 35 meter span crossing, because you just use the eye girder bridge or simple box girder bridge. So if you can't build or you can't use that one, that's why you're going to use this different form of construction, and they were expensive as well. This bridge is subjected to same as the loading previously, but the creep shrinkage and the thermal loading, the way is the stressors, induced stressors within the structure is significantly different to the others. The reason is this along the length of the structure, the stiffness of the member is vary. Therefore, the force transfer mechanism is not that uniform. So because of that, it's a bit complex, but you can, in the modeling, it's not a big problem for you to change the stiffness in your element like this beam. You can separate into exact same segment the way you build, and then you can change their properties one by one. Still, you can use the simple modeling, or now if you use the modern softwares, you can exactly model this one exact same way, same geometry and everything. And the the construction as a cantilever, and then the built on the camber, as I mentioned. Yeah, the issue is the no positive reaction most of the time. The analysis is exactly same as other bridges. So you have to support these bridges mostly on pot bearing. If it's a small spans, you can support on elastomeric bearing, and that solution could be a guided free or fixed free. It's up to you to decide. There is no hard and fast rule in here, because this bridge is very stiff. Therefore, the movement in this bridge, longitudinal movement and thing, they are not that significant, because of the force will mostly transfer into the pier in here. So you can have a very simple articulation system in the bridge, but to get that positive reaction is the key in this kind of a design and construction. You trust me, when you do all this calculation, you always see there is a positive reaction in here. Yeah, because when you cantilever this one, you put your barrier load and asphalt on the top, you will get that deflection in the sufficient deformation in here to create the positive deflection. But that is not the case, because you need to remember, in your structural analysis, you are not putting your post tension effect in here, your camber effect in your calculation. So that's why you won't see, you won't get the positive reaction at your bearings. Any questions? No. So up to now, we talk about the, without looking at the what is bearing, how it's behave, but we looked at, we need them to support, and then different bridges and different way of arranging them, different type of bearing we need to see. So the next couple of slides, I'm going to explain you what are those. The first and most common bearing type we use in bridge construction is the laminated elastomeric bearing. You can see on your right-hand side, the laminated elastomeric bearing is mainly made from natural rubber. You know about rubber, especially in Sri Lanka, is export rubber. Good one, good quality one. They use this one to produce bearings, natural rubber or neoprene. And the laminated elastomeric bearing, in the sense, this bearing is you get a series of the rubber and the steel, you stack on top of each other, you create this the process called vulcanizing the system. I think I remember when I was in the Bangkok, one of our, we build a lot of bridges, couple of kilometer long bridges. We use all sitting on elastomeric bearing, all the bearing custom made and we produce in the one factory. Yeah. So in Bangkok, I think they got a bearing producing factory. I'm not sure it's still there or not, but the process is you got a layer of rubber. It's like, I will give you the classic example. It's like you are preparing your sandwich. You got a bread, you got a cheese or ham in the middle. You put another slice of bread on the top. So if you want to make it higher, you put another slice of this. Keep building up. That is your bearing. So you can say that one, not elastomeric bearing, not the laminated elastomeric bearing. You can say the laminated cheese bread bearing. That this bearing is going to support the bridge. That bearing is going to fold your stomach. So that's the difference. So this bearing made from rubber. You know, if you made anything from rubber, it's flexible. It can bend. It can flex. So in order to talk about it, everybody knows about it, and it can be shaped either rectangle or they produce a circular shape like a cylinder. Yeah, it's available in the market. And the when you are using a bearing on the bridge is going to subject it to extreme weather condition. Lucky is not that much even in Australia or even Sri Lanka, but some part of Australia, like Cooma, you will get -10-degree temperatures during winter. If you go to like, let's say Canada, some part of Europe, US, you get a sub-zero temperatures. This material and everything, they have been tested. So I put a lot of some information, some document, I see NCHRP report regarding the bearing. If someone interested about to learn more, you can read that document. The elastomer, we call this rubber elements, need to absorb the sub-zero temperatures, so -10-degree. And then this should normally be designed to resist the SLS loading, the traffic transient loading, thermal, long-term effect, and the construction. These things we design. Another thing we need to design, we need to include this one in the construction tolerances. You will learn this one in the next slide. And this bearing is made from rubber. It allow a limited translation or the shear movement or horizontal movement, and the rotation. Yeah, rotation, it can flex. Yeah, the maximum rotation is around, I put the 1.5% radian mean 0.015, or someone else called is 15 milliradians rotation your bearing can accommodate. The bearing capacity will decrease with the deformation. Yeah, of course, it's made from rubber, and if it is deformed, if you just treat this one like the column with the axial load, when it's deformed, the higher the deformation, lesser the capacity. And the capacity depend on the bearing shapes. That means the dimension, the length and breadth of the bearing dimension, what we call the shape factor. Even the rectangular one, you can have a different dimensions. Like if you get a same size 600 by 600, 400 by 400, these are square bearing. So the shape of the bearing will have a different effect. In the same way, if it is a circular one, it is impact. As you know, the cube, we are doing the cube test, and we are doing the cylindrical test in the concrete strength. We measure from cube or cylinder. So the shape matters. As I mentioned, this one, the maximum vertical load this bearing can take is 15 MPa. Yeah, the maximum vertical load the bearing can take 15 MPa. The one reason is you can see this bearing, you need load from the top surface. The exterior surfaces are free to deform, free to bulge. The maximum vertical load it can carry in terms of the compression is not that high. It's available in rectangular, circular form. This is in the Australian standard. The bearing designs they customized. The designers can go and straight away pick that one from there. Even if you are designing in another part of the world or another country, if you don't have a standard bearing size, you can go to the Australian standard and you can pick that bearing. So it can be manufactured. It's not a problem. Another good thing, if you use the same bearing, it has been tested. It underwent through a significant QA/QC system, is all passed. So the bearing size is available as small as 230, 150 by 35 to 600 by 600 by 293. 35 is the thickness. Yeah, 230 and 150 is the planned dimensions. Yeah, 35 is the thinnest section you can. These are laminated elastomeric bearing because you need to have a rubber on the bottom, and then you need to have a top and bottom covers, normally 6 mm, and then you need to have an additional your steel plate. It's very normally it's 5 millimeter in Australian standard. Some designers use 3.2, and all these thickness add up together. You can have a minimum thickness. You can have a 10 millimeter thick elastomeric bearing. So your maximum height, you go up to 290. Higher the bearing, You can see from even from the graph, even from it's quite obvious. It's like slender. Then the carrying capacity higher is slender because it's made from rubber. It's supporting the bridges, high load. If it is too slender, there will be problem because of that. They have a limitation. So this is the smallest bearing you can get. This is the maximum bearing you can get. I put these numbers in the slide. If you are a designer, if you design this one, you can get some the idea about when you were designing things. The axial force, the maximum axial force, the maximum axial mean is a PO axial force it can carry. It's very easy. 230 times 150 times 15. That's the load. 451 to 5,046 kilonewton. That's the range. There's a significant range you can have it. Normally, I girder bridges and then super T girder bridges in the construction we use, they all lie within this one. But if you go to segmental box girder or box girder construction, you can use this larger bearing. 5,000 kilonewton is significantly large reaction. You can design the box girder bridges with having couple of few elastomeric bearing you can design. I put this one is allowed to deform 10 millimeter in minimum to 114 millimeter in maximum. The shear deformation, it will allow the deformation of the bridge. If you assume bearing and bridge go together like a rigid unit, if the bearing can deform 114 meters, that means your bridge deck can move, creep, shrinkage, thermal expansion, contraction, braking can add that together. So these are the range. So I just give you these numbers for you to get the global picture. What are the limitations you can work around with this bearing? Can be custom made. Yeah, the Australian standard, these custom made sections are available, but in another country, if you give the load, if you give the axial load, if you give the rotation, if you give the shear, then the bearing supplier will come up with the bearing design. And yeah, application for the larger size bearing are limited. That's what I mentioned, because this one we use the larger size bearing only for the box girder and voided slab bridges. Yeah, the elastomer thickness, the thickness in the middle layers between this steel, the elastomer, that thickness in a particular bearing, they are the equal thickness. They don't have a different thickness. One in 6, 1 in 9, 1 in 10. But some custom-made bearing, some designers, some manufacturers use that one. Nothing wrong with using that one. It's nothing wrong with using that one. So the bearing, they got a steps in 6. This internal elastomer thickness 6, 9, 12, 15, and 18. Yeah, and the steel plate, this thickness, the standard one, the suppliers sometimes used to design to ASHTO use 3.2, but you can design, still you can design this the steel member, but in the Australian standard is 5 millimeters, is all given. Otherwise you can design, of course. The design procedure is given in the code. And the circular bearing, you got the similar, the smallest dimension 240, thickness is the same, but circular bearing, the diameter you can go up to 880, and you can go a little higher depth. And this bearing, the capacity is higher than the rectangular one. You know that cube test as well. The rectangular one have a lesser capacity. It's like 20%, that's the number we use. 20% less than the cylinder one. Then the cylinder, the bearing have a higher capacity. It can accommodate little more higher movement than the rectangular one. And in other words, if you use the cylindrical one, it deflects in the same way because it's symmetrical. Along the diameter, it can deflect in any direction. So the again, the elastomer thickness, 9s, yeah, let's go in the 6, 9, 12, 3 millimeter step in the 21 is the maximum. And I put this graph in here for you to give you an understanding. If you increase the thickness of the elastomer, because we are talking about rubber in here. Thicker, it's easy to compress, it's easy to deflect, right? If your thickness of the rubber, the elastomer is 6 or rubber pad is 6, the effective compressive stress or modulus we call is 700. If we go to 9, is reduced to 421. 12 is go to 270, and if you go to 15, 186. It's going down. I put this easy value. The reason is the easy is the property when you apply the vertical load on the bridge, how much your vertical compression is going to be. You can see you got a thicker the elastomer inside this laminated elastomeric bearing, the higher your vertical deformation of the structure, higher the vertical deformation of the bearing. In addition to that, overall the superstructure. Please keep that one in mind. It's going down in a significant way. The vertical stiffness you can change in here. I think this is the very common thing. Elastomer properties is measured in terms of the hardness. In the rubber, we measure the common factors, the shear modulus, quite common hardness 50 or 60. Elastomer properties we use, if a hardness 50, the shear modulus is one of the key parameter in the bearing design is 0.69 MPa. You can see they are very small compared to steel concrete. Another thing is 0.9 for hardness 60 elastomer. But you can see in the both cases, the bulk modulus is the same. Any question on bearing properties? This laminated elastomeric bearing? Okay. Then I jump into next one. I put this one in here before I go to the other slide. So you get a laminated elastomeric bearing. What that carry? It's carry all the vertical load from the bridge girder reactions. SV. When you apply that vertical reaction in here, you saw from the previous slide, the deformation pattern is way because this inside this rubber element is going to complex. So there will be a deformation in your steel element as well, but compared to rubber one, that is very small because if you see the E value of steel is 200 GPa or 200,000 MPa. So that's significantly large. Because of that, deformation is very small. So mainly the elastomer, it's compressed the rubber section. That's one, compression of elastomer. Because you got the longitudinal loading, that's where the bridge long structures we talk about all the time. That longitudinal load, what will happen? It will be applied on the top of the girder. It's like a friction force, like a shear force. When you apply the shear, you can see the shear modulus is very small in this one. If you go to concrete, you know the E divided by 2 times 1 plus mu. So 1 plus nu, the nu is 0.2, then 1.2, 2.8, or if you say 2.4, if you say divided by 2.4, you can say it's a significantly large. You compare this one, this in the rubber is very much less. So therefore, when you apply even a small amount of load in here, this will deform. We go back to this slide, you can see there's a restriction in this deformation, right? The shear force, the deformation and the shear force and shear modulus, they're all related, linearly related. If you multiply the shear modulus time area, time the deformation, you straight away get the divided by the thickness. If you can straight away get, you can get the, if you get the shear deformation divided by the thickness, you get a shear strain. If you multiply from G, you get a shear stress. You multiply from the area, you get the force. You can calculate, but you can see these numbers. They are not meters, like 110 to 1114. That's the largest we can get from this largest bearing. So this force is not that significantly large. So that create, because of the shear modulus is low, significantly large deformation on the bearing, right? In addition to that, because of the girders is rotate all the time, then this one it will rotate. It to allow the rotate, the bearing has to deform. Please forgive with me my diagram in that way. So when you combine all these three, this is what you get at the end. 1, 2, and the rotation 3 in here. This is what is your bearing actually look like. The loading acting on the bearing is shown in this in here. Vertical load V, horizontal load H, movement in and out, and the girder rotation. That's all combined. You end up having this deformation. So when you are designing a bearing, when you are selecting a bearing, what you try to do, you try to get these three accommodated together. So you need to have some understanding about limitation of your bridge, deformation, reactions, and everything when you are working and selecting your bearing in here. That will give you a good guide. That will give you a good guide. So of course, when you calculate, you need to, these are talk about SLS load. You need to accurately calculate your vertical load, horizontal load, your rotation, the movement, creep, shrinkage, and then all these things you need to calculate. You need to calculate. Again, in addition to this one, if you get the three-dimensional model, your substructure will be deformed. So then your bridge bearing will have some impact on that one. Please note that this load will be transferred together because the bearing physically, I should say the word physically or mechanically, the bearing and substructure and superstructure, we combine them together. The physically, in the sense it's based on you just put the rubber on top of the concrete, and then you just let the vertical load, that friction to develop that load, or else mechanical in the sense you have a restraining system. For example, you put dowels, you put the boxes to keep the bearing in position and restrain and link together. The mainly substructure is not the big problem, mainly the superstructure. But you will see on the previous pictures, the bearing can walk along the surface. Because of that, it's very important to understand we need to lock the bearing on the superstructure mechanically as substructure as well. So the forces from the superstructure will transfer to the substructure, to the bearing, then to the superstructure. Sorry, then to the superstructure, then to the bearing, then to the substructure. Yeah, we can mechanically design that one. Yeah. Any question in this slide? No? Then I will just quickly touch with the pad and strip bearing. I think in here, I forgot to tell you, the design life I mentioned before, design life of the elastomeric bearing is about 35 years. If you properly maintain, you can achieve more than that. The other thing, the plain bearing and the strip bearing. The strip bearing we mainly use in the bridge approaches, because bridge approach is part of the bridge because it's sitting on top of the curtain wall. It's a continuous structural element, so you need to have a continuous support. So we use the strip bearing to support the approach slab. In addition to that, we can use the strip bearing to support the plank bridges you place side by side. And from the strip bearing you can make a pad bearing, but they are unreinforced. They are not laminated. They don't have a steel reinforcement in the middle. They are natural rubber. Only the rubber, they are thin. And you can use to support the spring. Even you can use this, we used to design. It's not allowed now. Previously, we used in the design using a lot of the space plank bridges, even using the pad bearing. Yeah, there is no reinforcement. we use in bearing approach. Plank bridges is quite suitable for short span bridges. Plank bridges in the sense you can use for the, like this picture, space plank bridges. And even you can use if you are designing the fully integral bridges in the short span, you can use the strip bearing in there. And the maximum compression in this bearing is only 5 MPa. This is just the natural rubber. And this 5 MPa is depend on other factors, the shear modulus and the shape factor, the shape of the dimension of the bearing that you all learn when you design the bearing. And this bearing can achieve close to 100-year design life. So if you design the bridges with the proper design, using a strip bearing is maintenance free. And the standard thicknesses vary. If you go to certain application, you can get the bearing as small as 3 millimeter thick. But normally in the bridge supporting system, we use 20 to 25 mm thick bearing. The maximum rotation is the half of this, half of the thickness. That is the quite simple norm. In the elastomer, shear strain is 0.5. So that means if you get any bearing, if you get the thickness of the rubber, forget about the thickness of the steel, any bearing, if you add that total together divided by 2, that is the maximum deformation you can get in your bearing. Yeah, that's sent in the design standard as well. And then this the maximum translation you can get, because the maximum thickness is 25, is 12.5 millimeters. It can accommodate with higher rotation. Yeah, the main problem in this bearing is because when you are using pre-stressed concrete bridges, if the span is longer, the hogging effect is significant. So that create the bearing, if it is hogged too much, the bearing is not going to touch. The girder and the bearing is not going to touch 100%. The contact area will be reduced. That's one of the quite problem, is hard to solve. That's one reason the clients, they opt to use the elastomeric bearing in place of the pad bearing or strip bearing. Yeah, normally they use the 60 hardness 60 for the strip bearing, and these are the parameters, because it's got the different dimension and the length. It's got the modulus of elasticity is quite higher compared to the elastomeric bearing. Yeah, and I put this information for you for you to understand. If you place the rubber on top of a different concrete surfaces, the friction coefficient you can assume, and you need to follow the guideline given in the codes. Yeah, you can see if you put this the hot dip galvanized, that the friction will reduce to 8%. So that is what normally we use, the common practice in Australia. We get the bearings sitting on top of the hot dip galvanized. So because of that, you need to have a mechanical restraint system to transfer the load from superstructure to substructure. So that's why we have a boxes in there. That is the reason. So if you are just putting the bearing directly on top of the rubber, this friction coefficient will be 35% from the vertical load, maybe quite sufficient to translate the load. But the issue will be if you leave that one alone, the hogging, because of the hogging and the creep and shrinkage effect, if the hog in the beam is increased, then the bearing, the girder will tend to slip over the bearing, because your contact surface area, you can't calculate properly. If I give you the one, the way to check whether the bearing and girder is touching the proper way, you can use your A4 sheets, or even you can grab the piece of paper from your a notebook. You can slice that one in. If you get an A4 sheet, the normal A4 sheet thickness, I think it's vary from 250 micron to 300. From that one, you can calculate the gap in between the bearing surface and the, when you place on the girder on the bearing, you can see when you insert the A4 size paper, you can calculate the gap, how many number of papers you can insert that one in through the gap. You can see the area where it's not going to that area. That's the way normally the way we test the surface area, the bearing is not touching, and the gap between the bearing and the it's a very simple way. You can use a quite complicated way to calculate that one, but a simple way to check that one. And this is I learned from one of my friends who supervised about 100+ bridges in Australia. He just told me, Rohit, we have a problem this one. This is how we're going to test it. I was quite shocked to see that one. Actually, that's true. Yeah. And this is something you can do quite easily, but don't worry about that. If you have a problem like that, you can fix that one later. Any question about this, the two type of bearing and their performance or anything? No? Okay. Then we go to pot bearing. We talk about this one a lot. The reason I put this pot bearing before, I think I discussed with you about pot bearing before under the bridge element as well. The pot bearing, we have a few types. One is the free sliding, is free to slide any direction, go any direction. And the guided is exactly same like this. It's allowed to guide. The guided bearing, in the middle, we have a piece of block on top plate on the bearing, and we have another plate, and we have a groove in there. We let the bearing to guide along that one. We put the Teflon in there. That's how it's moving. I'm going to put the actual bearing shop drawing there. You can see that one. Yeah, exactly the same way. It's guided. It could guide in the longitudinal direction. You can design your bearing to guide on lateral direction. These bearings are custom made. They will produce the way you want. And the bearing is fixed. The way it's fixed, I'm sorry, I didn't have that symbol need to be the red, the circular one, fixed bearing. It's not going to move anywhere, right? It can carry large loads. It can accommodate more rotation than the elastomeric bearing. Elastomeric bearing 1.5%. That's what I use these numbers like that. You can remember easily 1.5 against this bearing 3. I think, I'm sorry, I think this is not right. The plank bridges included space plan because when I'm developing this one, I'm working after my office hours in the late night. When I'm developing, I get the blocks from the previous one I edited to make it all consistent. And I think this is wrong. That bullet point, please delete. Yeah, it's allowed rotation up to maximum up to 3%. Bearing can accommodate large deformation. This can be designed to any large deformation. I think we use as large as 700 mm. I think if Sean is there, I think he was involved in modeling that bridge. We designed the bridge as long as 700 millimeter deformation with the sliding bearing, it's a pot bearing. Yeah, you can get that one, no problem. Yeah. I will put some detailing in the shop drawing location. You can see it slide one plate on the other one. It can. And it's very common in the box girder, balance cantilever, cable stay, all large bridge construction. We use the pot bearing. It's not common in the Super T or I girder bridge constructions or steel bridge construction, not that common. But if you want a steel box girder, sometimes you can use. This one mostly common, and it can be made. It's a custom made. Yeah, it's a custom made. You can give the design information. For example, the vertical load. What is your horizontal restraint requirement? For example, if you are designing a free sliding bearing, you need to tell the manufacturer how much is going to slide. 100 millimeter. My bridge need to be moved. Then I need to be slide 100 millimeter. So my vertical load is 4,500 kilonewton. So you can give that one, then they will come up with the bearing design. And in the same way, if you want to design a restraint bearing, You say, okay, my longitudinal restraint 600 kilonewton or 700 kilonewton, including breaking the creep shrinkage effect. My vertical load is 4,500. Then they will design that one to restrain that load. In the same way, in the guided bearing, you can tell them it need to be move 100 mm, because if you are free bearing in the same location, move 100 mm, then your vertical, your guided bearing need to accommodate the same. But you can give the information, they will produce to you. It's custom made. And the this maximum compressive strength, because this bearing also got an elastomer inside, can go up to 50 MPa. Why is it? Because the elastomeric, the pod bearing is a pot, like it's a bottom cylindrical element, top cylindrical element is put inside the other, right? The elastomer, your rubber section is confined within that space that can generate higher compressive strength. That's the difference in here. This one can go to 15 because it's unrestrained. This one can go up to 50, it's restrained. It's the same principle we use when we were designing sand jacks. That not sand bearing, that bearing we call sand jack. Yeah, that temporary bearing we call sand jacks. That's the word I could remember now. I'm sorry, I used them so many years ago. The capacity of this bearing can go to many amount. If you go to different manufacturers, some manufacturers, they manufacture this one like a megabar up to 75 meganewton, they call 75,000 kilonewton. You can go to any amount of the capacity. Yeah, it's not a problem. Some designers, they design some manufacturers, they can go the restraint capacity of the bridge, they can design up to 30% of the vertical load as significantly large. Yeah, because these are custom made. You can go to really big extreme. The only thing, cost is the big thing. The size requirement is big thing. Yeah, that's the one thing you need to be mindful. I didn't put all this information here because I already put them in the reference document. When you select your bearing, you need to be mindful because these segments are really big. 800 by 800, 900 by 900, 650 by 800, really big. Whether your substructure, your girder, have a sufficient width to anchor that bottom plate onto your substructure. Because as I mentioned all the time, your bearing, you need to be mechanically anchored with your superstructure. Yeah, using dowels and things in here, whether the bridge girders have a sufficient dimension or not. This is quite important when you're selecting them. I put here bearing design must complete prior to the construction. It should be, because this bearing can always be connected with the superstructure. Normally they use bolt, or some designers, some suppliers, they use like a pressinet, they use a stud. They use the stud to attach. If you are a building designer, you are quite familiar with this, the way you use stud in the construction. I think we use the stud. So normally we use the bolt, because to put your post tension, your reinforcement, this bolt location, you need to be exactly, you have to fit, because your bearing, you will go and assemble, you tighten the bolt. Because of that, your bearing, you're going to custom made, because you give the design, the supplier, the loading and rear requirement, they will design your the bolt size of the bearing. Then you need to use them before it need to be concluded before you start building the bridge. Building the superstructure and substructure, because both of them you need that one. Some designers, they go to a particular supplier, they look at their catalogs, and then they keep the oversized hole, and then they put this bolt and anchors and they grout it. There are so many ways this one can be built. there's another thing, we preset this one. The one example is presetting is, let's say this is a bridge, right? Then this single span bridge, when I post tension, right? When I post tension, this is going to move, it's going to slide. When we apply this, the external post tension, if it is slide, if we move, then you can do in your bearing, especially this is quite complicated when you go to the stage construction, segmental box girder, or the continuous span box girder construction. You can set your the bridge, the bearing little bit back. So when you stress, the bearing will be pushed to the right location. This presetting, designers need to calculate and give to the bearing supplier, and they will preset this one in a proper way. When you design and when you construct, you preset that one, and then the after construction finish is come to the center line, like center line, bridge center line, and the bearing center line, they all match together. Yeah, because it can go around arbitrary. You can get the combination in the curve girder bridges and things you can utilize. Any question about? Any questions? No, then a spherical bearing. Spherical bearing, yeah, the same family of pod bearing. I explain it to you. We use once in this industrial ring road bridge. You can see in the background, in my background, that bridge, that carry a higher load, as well as it can, because it's spherical, it can tilt in any direction. I will put that drawing in the, I will put that picture for you to see in a big scale. This gantry, 1,800 ton, supported on these bogies. There are two bearings in front, two bearing in the back. This bearing we made from spherical bearings. If I can find the picture of the actual size of that particular spherical bearing, I will include that one. You can see the actual shape, size, and things. Yeah. This one, again, capacity and rotation quite high. You can make it larger. The good thing is this bearing, like the project industrial ring road, this fellow allowed the bridge to rotate and deform in a very flexible way. But you know, the bridges, when we design, we can't let that one to go up and down like that. We need to control that movement. That's why we use the lockup devices and the kind of thing to make it in the guide in the right direction. But this fellow will do the job. It will let the complex geometry, complex deformation to be absorbed. Yeah, and it can carry very high load. I mentioned this one we use in the gantries as well. And this one I mentioned, the maximum compressive strength, it can go up to 120. Yeah. In the contact surface, we put the Teflon in there, that can go up to 120. Even you can see, because of the spherical surface, this is a cylindrical surface, this is a cylinder, but 15 rectangle free body to go up to 15 to 50, it can go up to 120. Yeah, it can go up to 120. It's quite high. And and this bearing also has got a lot of different application. This is the one element in the bottom. You got a steel, solid steel element, and then you you grind that one. I put the Teflon in here. You got a one in the middle section. The number 3 is a spherical bearing plate, we call, and in between we have a Teflon, or this Teflon element, the number 2 element, the horizontal Teflon plane, mean that allow your bridge to freely rotate, to freely move, depend on the way you want to move this bridge. They will come up with the design is guided or fixed or free, and any direction. You will see the pod bearing shop drawing I'm going to share with you, so then you can see the same principle apply in the spherical bearing. Even if you go to any supplier, they have a 3D pictures. They have an anatomy of these bearings. You can easily read them. What they do inside in here, what we got a piston. That piston we replace with the spherical plate in here. That's the difference between these two bearings. Yeah. Any questions up to here? Yeah, I'm not going to discuss with any other type of bearing. There are so many types of bearing you can come across, but they are not that common in the modern day bridge construction. But if you are inspecting, you are checking very old bridges, 50, 60, 70 years old bridges, there are so many different kind of bearing, what they call knuckle bearing and other thing you will come across. The back then we use. So yeah, so if you need, I think I can provide you a lot of design literatures for that one. Then if you don't have a question, do you have any questions? If you don't have, then I will jump into quickly to the joints. This one also, I have one document I have put in the reference folder there. You can read that one. I'm not going to spend a lot of time about the bridge joints. There are so many joints in the bridge. What I will do later, I'm going to put one bridge joint with mark all the joint, you can say. I have some example in here. When you say joint in the bridge, what you always see, expansion joint, right? The very common expansion joint in the barrier joint, the one on the bottom, it should have been come on the top, barrier joint. Then that's the movement is about maximum 20 mm. And the strip seal joint is made of, because these two entities on either side, they move, right? One is fixed, the abutment, one is moving. It's not the same way if you put in the middle of the bridge, got so many span. Like if you got a 10 span bridge, you got the bearing in the 4 span, every 5 span. So then the both side is moving. So then these two elements are moving. Then this strip seal in this rubber seal in the middle, move in and out, move in and out. Why we are having this rubber seal in here is mainly protect the water. Because if you do not have a seal in here, what happened during the rain, there will be the waterfall across the expansion joint. And yeah, normally you got a waterfall in most of the bridges built with the strip seal underneath the bridge. Sometimes you're lucky enough you not get one in the middle. Most of the bridges, they got one in the middle as well when they were connecting this strip seal segment together. And then of course at the corner where I interface with the barrier, you get a free waterfall there in the rain in these strip seal joints. And then the next step, the higher we use the finger plate joint, the finger plate, or they call the skew saw joints, and these joints can accommodate higher deformations. This one will be like 2 fingers is going in and out. The only thing in here, if you see the strip seal joint, because it's the rubber seal in the middle, if this bridge is moved laterally a little bit, it's not going to affect that much. But you can see the finger plate joint, if this one move laterally, these fingers will jam. Then the bearing will not work in a proper way. And the other one, we use the module expansion joint. Module expansion joint, exactly the same form of seal joint. There are many put together. The way we develop this joint, you can see the same way. They have this beams in here. They got a multiple, I should say, it's not exactly the same. The same way, same repetition, multiple strip seal here. And to support this section, the modular section, we put the transverse beam across the bridge from this side to that side. To allow the bridge to move, one side we fix, another side we make. It's like a piston, go in and out. That's the way we detail. I will put this information for you to detail, or even if you Google and see the catalogs, you can see them. When you go to the These, apart from this joint, the construction joint is a common one. The contraction joint, when you are building slab, you know, the if you want to build the slab 6 meter in width, 30 meter in length, you're not going to go and pour the concrete in a one go. So you're going to cast this one in interval. So you're going to put construction joint, contraction joint, expansion joint across to make sure that you're not going to get your deck crack. You allow that scrape shrinkage and other deformation in the bridge to accommodate. You provide those joints in the bridges also, you get them. And the barrier joint, of course, we in the rail, because if you have a rail on the top of the bridge, like we saw some bridges, the bridge barrier consists of segment of concrete and segment of railing. The bridge can accommodate hundreds of millimeters of movement, then this railing need to be designed to accommodate that one. So in the bridges, we have a drainage, then the bridge is moving, drainage section is moving, then you need to have a joint. For example, if you have a drainage going across the expansion joint, you may have to sometime. So then you need to have a joint in the drainage pipe, same as your bridge. Otherwise, the drainage pipe will be crushed or will be open up. Yeah. And then joints on services, same as the barriers we normally use to get services across. You put the conduit in there, unless otherwise you put the gaps in there, because your service provider, like a utility providers, like telecommunication, especially the electricity service provider, they don't like those gaps. You need to have a continuous conduit to for the cables to run through. Then you need to design those gaps exactly. The conduit going across this joint, then you need to design the expansion the joint to accommodate that one. These are the small thing in this bridge. There are lots of 20, 30 if you can pick joint detail in a bridge. I can't explain each and every one of them to you, but I have some example. I put the design lives in here. As I mentioned in my presentation at the beginning, design life, though I put as a separate dot point, but I'm going to discuss together. Yeah, joint pillars in the sense, in that barrier joint, you will see this one in the next slide. We put the pillars and then you put the backer rod, then you put the sealant around. So these pillars, because sealants are expensive and otherwise it costs you fortune. That's why we put the pillars. They have a very low, the design life is not high, 10 years. And joint sealant, these exterior surfaces, they have their design life is quite less. The reason is this exposed to UV. And the expansion joint rubber, this rubber extrude is only 40 years. The compression field joint, this joint design life is 40 years. Yeah, then every 40 years you need to replace. And I forgot to explain you one thing. In this finger plate joint, because it's open all the time, because the water is going across the joint, then to protect water going across all the way like a waterfall, you need to have a drainage underneath this finger plate expansion joint. So please remember, you need to have a drainage. Normally with the supplier, they send it to you, but if your drainage designer decided it's not good enough, it's not okay, you have to design that one. Any question in this slide? No? Then I have a couple of example, different joint. These are the joint you come across in a bridge. Quite simple joint. This is one on the top right hand corner. This is even if you put eye girders with the plank, or if you put the bulb TB girders in the bridge, there will be a small gap between these two precast elements. So when you are casting your deck on the top, that is the concrete when you pour, if you leave that gap in here, right, the concrete slurry will come down through this one. Yeah, up to a certain extent. Then that will create the weaker concrete segment in here, right? Another thing that if you go to durability, that will create the durability, different exposure environment, because in here and there, if you get the exposure environment of this bottom decks in here is enclosed, and this is the exposed environment. These are the reasons. So if you put the durability part of the side, so to prevent the concrete leaking across, you had to put a tape, that one, along the full length of the bridge. The reason we make this one bit of a dip we give here, one reason, when the people are walking around on the top, it's not going to crack along that one, because if you put horizontal, this one is develop tension, you can find a crack. So put the tape, but it's still not working while construction, but this will allow that, and plus it will provide the proper concrete cover and proper bonding the concrete in area. I think that one of the main reasons, I should say, not the durability reasons, the main thing is to prevent this not cracking while the workers is walking on the cross. And the other one, if I go back to this precast barrier construction, this is the concrete deck, and this is the precast barrier I mentioned to you before as well. Then we put the stitch for. You can see this create the construction joint across that point. This dotted line in here on the base of this stitch for construction joint. And you can see in here, your deck in here, there's a construction joint. Over the time, creep, shrinkage and thing, this can be the open up and you can have an issue. Because as a good detail, we have a joint detail in here. So we cover this one with the butadiene tape to make sure that it's waterproof. The water is not going across in here in the future, and then this reinforcement is not going to corrode. This is one of the joint. Yeah, it's not the bridge joint, it's one of the joint. Yeah. Another thing, if we get the precast element, this is the length is in maximum length in order of about 5 meters in the because of the construction, because of the lifting and placing those restraints. This joint, as I mentioned in here, you got the sealant around to make sure you covered that one, this joint. This is the detailing of that joint. You got a backer rod in here, because the backer rod, to make sure that you push that one across, then you put your sealant again, that one. In some instances in the bridge deck, if the two deck is there, if there's a joint, if you want to overlay the asphalt, remember when you overlay the asphalt on top of the deck, the temperature is about 150 plus degrees. Because of that, whatever you put on your joint there, to make sure that need to be take that temperature, can absorb that temperature. So you can create joint between, if you need to, the deck slab. There are so many joints. According to your design, you need to identify them and you need to design them. That's very important. Any questions? No? So then I'm going to a joint between the approach slab. If I just explain a bit of approach slab, we first construct, you can see in here, we construct plus the head abutment, right? On the other side, we have a superstructure girder. Sorry, I didn't show that one. And the approach slab, the end, because it's different country to country, you have a different approach structures. This one, we got a wing walls in here. Then we build the approach slab in between the wing wall. So if I cut a section in here, the wing wall in the vertical section, the wing wall is in here and the approach slab is interfacing that one. We not build approach slab, wing wall integral together, because approach slab is subjected to the traffic loading all the time. It's in the ground because the wing wall is attached to the bridge abutment that is sitting on the pile. It's rigid compared to this is the approach slab mostly sitting on the ground with the existing soil, and it will subjected to a differential settlement between approach slab corner of the approach slab and the bridge abutment. So because of the settlement, approach slab will rotate. You see, when the approach slab is rotating here, you need to allow, as I mentioned before in the semi-integral bridges, so any bridge, you need to anchor this one in here. You need to allow a dowel in here, because especially the approach slab, if there is a break in, if you not dowel this one in here, your approach slab will slide across. So you need to provide the dowel. You need to prepare the special joint detail in here. This you can see the bottom piece in here, that's a strip bearing. And then you get your dowel embedded with the curtain wall, and then it's come up a bit higher within to the approach slab. And then you put it the rings and the oversized cap to make sure that you allow certain rotation in your approach. These are the minute detail you need to develop and build on your bridge. Otherwise, what happened in this bridge, you build and leave the bridge, it will crack. Okay, it will crack. Yeah. So the other detail between the approach slab and the approach slab and the wing wall is pretty much easy, because there are two different concrete elements. Normally we put the polystyrene in here. On the top, we provided the sealant on the top. Yeah, that's normally we do. The abutment curtain wall side, the approach slab. I just put this one. Another thing, I just put this one in here. The construction joint is very common. Every one of you know that one if you are designing any construction. You've got a construction joint, because we build element by element. So this joint detailing will decide the way its load transfer mechanism. Again, the requirement for the waterproofing and etc. Any question in this one? These are very simple detail, but you need to think a lot, because the bridge design is not designing the girder, not designing the pile, not designing the column, crossbeam, reinforcement and that thing. The bridge design is much bigger than that. These small elements will decide the way your bridge is performed. If you not properly detail and if you not properly build them, you can build your bridge. What will happen, because of this complex deformation and loading, it will crack. It will have a lot of issues. Yeah. So you can see the one reason I explained that semi-integral bridge concept in here. This approach slab and other thing, differential settlement, if it is rotating here, this will bend. This bend will, after this, the element is bent, then your bridge behavior is totally different, because some structures, if you work on the flexible ground, this settlement is quite significant. This pull everything down because of this dowel. Yeah. And the other element, I think there are a lot of joints and things. I will put some example over there. You can read through a bridge sample drawing set. You can read through it. You can understand when you read the drawing, you color that one. You say these are the type of joints. So in the assignment, I will ask questions. So the another common course in the bearing replacement. So you had to use the bridge built with bearing, except the one if you use with the strip bearing, or if you use the integral bridges, fully integral bridges, the rest you need bearing. So when you were having when you support the bearing, I said design life of the bearing 35 years, design life of the bridge 100 years. So then you have to replace a couple of times, at least once. If you properly maintain, at least once. If you not properly maintain, if you're not properly designed, if you're not properly built, maybe couple of times. So when you are designing, when you are replacing the bearing, what you need to do, you have to, because the bearing is your support. It's take all the load. So if you want to replace them, you need to have a temporary support system. You need to have a jacks. You need to have a jack to support the bridge, right? Then it's up to the road authority to make sure that whether you want to close the road to replace the bearing, or you let the traffic with the controlled traffic environment on the top of the bridge. But if you talk about a expressway, motorways, you can't close them, because the bearing replacement is not going to happen like it just it's not happen like a couple of minutes time. It's a very complex process. You try to jack the whole bridge. It's involved a lot of safety, a lot of preparation, a lot of work. So because of that, it's take time. So at least a couple of weeks. Because of that, you can't close your bridge for a couple of weeks. So then as a designer, you need to design your bridge to replace the bearing. So if you not design your bridge to replace the bearing, that means you haven't finished percentage of your design. So the design is a must. And the requirement can be dictated by the road agencies or dictated by the design standard you're going to use. Yeah, it's depending on that one. This is the one example in here. The reason you can see in this example, we have a, as I mentioned before, lateral restraint block, right? Because of that lateral restraint block, the bridge jacking principle we have to use is not symmetrical. Another reason, we use the cross beam to jack the bridge. We use the end cross beam in the bridge to jack the bridge, plus the end cross beam will allow to less the deformation of the structure at that particular point to reduce the bridge deformation, girder deformation at the end of the girder. That will help your bearing life and the design. So the cross girders is internal. They are, like we say, internal diaphragm. So they are located internally. Because of this, this one, sorry, I forgot to label that one. This one is lateral restraint block. So because of that, you can't put any bearing in here. You can put the flat jack, is really difficult. So you can see your bearing arrangement when you are temporary state. For example, in here, this whole girder is cantilevering from this point. This makes sense. It's clear, right? This point in here, this whole structure is cantilevering. So you can't let the shoulder to people to drive on the shoulder. You have to close the shoulder while you are jacking the bridge, because if you put your traffic at this end, that will generate a lot of forces in here. It's very unstable, because when you are jacking the bridge, you use the jacks. So jacks can't accommodate a lot of rotation. They can support a lot of vertical forces because it's hydraulic jacks, right? The hydraulic pressure can support, it can accommodate certain amount of tilt. Yeah, if someone need to read about this thing, just go to the NAPAC, one of the hydraulic jack suppliers. You can read, there are a lot of information in their catalogs. So this is cantilevering, and you need to set up your number of the location of the jacks. You can see the jacks arrangement, they are unsymmetrical. Therefore, reactions in these jacks are unsymmetrical. While you are replacing the bearing, your cross beam is we jack from the cross beam. All this load transfer to the jack via cross beam. Then you need to design this diaphragm or cross beam. In this diaphragm, you need to design to support that load. That's quite significant. Because of the dimension, the size, the spacing, this element will be acting as a non-flexural element, working like a strut tie model, but you need to design. You need to provide proper reinforcement. Yeah, if someone think that because another way the people design the bearing with the wider headstock, you can jack your bridge in front of the bearing. You can do that one. So then you need to have a wider headstock, wider column. So that is some designers opt to that one, but it's one of the standard practice in Australia. We design in between the diaphragm, but we design the structure to take that load. So then during the bearing replacement, bridge open to the traffic with reduced speed. And normally the bridge deck should be able to lift at least 10 millimeter to replace the jack. Because you need to replace, you need to clean, and you have to come back and you have to put the new bearing in there. And then, as I mentioned before, this semi-integral bridges, if your bridge you are working with these doubles, integral bridges, of course, you don't want a bearing, but semi-integral bridges, this 10 millimeter lift is a bit too risky. A bridge will be on jacks during replacement. Cross beam or this diaphragm should design during bearing replacement for this bending and shear. And then the bearing reaction and pressure on the substructure, you should mention, because otherwise nobody knows how much, what is the size of the jack they should use, right? You have to write what is the reaction in this particular bridge for this particular configuration. So you don't want to write in each and every point. You can give the maximum, or if you will, you can say 0.1, 2, 3, 4, 5, you can tabulate. So that will allow the bearing replacement. The contractor, he can select the right jack. Please note that the bearing replacement will happen after you retire. Yeah, even if you are very young, design this bridge, the bearing will replace after 35 years. Yeah, then yeah, most of the time, even if you're not retired, you are not in a position to do this kind of a calculation. You will be tell the other people to do this calculation, because that you won't get involved at all. So please, you need to write the reactions in the drawing, and you need to show the jack locations and the other information, because when you are jacking, there will be a bearing pressure, and you need to see whether these locations sufficient to put the jacks and the pressure on the surface of the concrete. Because if you have if a concrete strength is 40 MPa, your bearing pressure is about 60 MPa. That doesn't work that way. So you need to check that one. You need to make sure that you all work, because otherwise what happen if you move your bearing closer to the edge, and if you higher pressure in here, the concrete will crack. And so while you are jacking the bridge, that's another risk if you jack in the front of the bearing, because of the concrete cover, if it is higher, if you're not properly reinforced and detailed in here, what happened at the corner, the high pressure, the concrete will slip with if you use a higher concrete cover, like for example, C1 environment, you need to have like a 60, 70 millimeter concrete cover. Then if it is cracked, then the bearing might rotate and the jack will rotate and fail. There are so many elements you need to consider that one. But anyway, this bearing replacement, the experienced contractors, they have been doing this one. They know exactly. But this information you need to provide in the joint. Any question about the design of a bridge for bearing replacement or information you need to put? No? Okay, then the last on the the special consideration topic. This is the one thing, the very important, the bridges with the link slab. As I mentioned, I think in the previous example, you can go up to 250, 300 meter length with the debonding. I show the calculation in here. If you leave that gap 50 mm in here, the axial stiffness is really quite high. This shrinkage forces, the creep shrinkage thermal will crack the bridge in here. Because of that, the link slab and anything we attach to bridge deck, we debonded. The way we debonded in here, this is our top of the girder, and then we put the 10 millimeter thick fiber board, thick board. It's not plywood exactly, similar to plywood, thick board in here, and then we debond the concrete deck. This length is about 1.9. I think if someone is interested, there is a paper, I think, because in Bangkok, they use link slab quite a lot. There's a paper about that one, but that link slab is that paper is not related to this Super T. That related to eye girder. With you remember the I put the particular one. The eye girder is sitting on either side of the cross beam, and the link slab is open, about 2 meter in length. Yeah, in that for that particular analysis they have. But anyway, if your girder placed like this in the Super T kind of a construction, or if you use the your headstock and you place the girder directly on top of the headstock, you will get this situation, any type of girder. Then you need to debond this one. The debonding length is about the 1.9. So during construction, what we're going to do, we're not going to pour the whole bridge at one time because of this debonding, because of the creep shrinkage. To minimize that, we construct the bridge in terms of the segments. That segment, you can see the construction joint we locate about 1.7 meters from the center line. So you cast your the deck sections first, and then you cast your a link slab section, this one. So these things you need to document in the drawing, because otherwise the contractors, they don't like to have a construction joint on the deck. That's really a nightmare. Yeah, it's in different countries allow different form of construction joint. They call the expanded metal construction joint. This is allowed in quite common in Asia, but I used this one before. But no harm. But in Australia, we don't allow that one. In Australia, the construction joint you have to prepare with the timber. That's really hard. Because of that, this is very hard to build and take a lot of time. It's very expensive. Because of that, because it's a labor incentive, contractors, they don't like. So because the expanded metal one is not the preferred one in the road agencies in here. Yeah. The other special consideration I mentioned, if you use the floating type bearing long length, because of the bridge is moving in and out because of the earthquake situation, I don't want my expansion joint to go and jam, especially if it is a finger play the joint. I don't want that one to go and jam. I don't want my bridge to the bearing to slip. I don't want my bridge girder to go and engage with the curtain wall. So we just put the longitudinal restraint in here, restraint block. This is the very simple to design. You can see what is the maximum gap I allow my bridge to move, because as I mentioned before, when you build the bridge, is always getting shortened because of the creep and shrinkage. Longer the bridge is longer the shorten. So then the thermal effect will basically disappear. If you do the calc, it's very easy to see. Thermal expansion will be disappear. This gap, because of you need to decide this gap because of the earthquake situation. You can do analysis, you can calculate, you can even do dynamic analysis, but you don't know exactly how much is it going to happen in real earthquake situation. Because of that, for the low-arm bridge, I recommend to put the buffer bearing we call on the back. This is a piece of concrete. It's attached to that one. You just need to N16 or N16 U-bars at 150. That's a very small crowbell. You can have a piece of rubber. You saw the strip bearing piece. You can nail that one into the this element. Or there are some epoxies you can use actually to attach that. And then because this is exposed to lot of HV, because of that, most of the road agencies, they don't like epoxy attachment. They need a mechanical attachment. You can develop that one. So that will prevent a lot of harm, because this bridge never going to go and dislodge, because you lock from both ends. Yeah. If there's an earthquake, it will move to that end. It will hit. It will return it back. Because if it exert a load in here, the substructure behind is quite it's strong. It can absorb that load. It can absorb that load. So because of that, yeah. And these are the special consideration. I just put it in here for you to just to keep to get this thing when you design and detail a bridge. Because these are the thing, because it's not in the textbooks or anything. These are the things we develop with our experience and the finding a solution to the different problems. So if I just explain it to you, this dot point separately, debonding, the slab and the barrier also you need to remember debond, because to make sure that, because if a barrier is attached to the deck, the deck will move, but the barrier can't move, then it will be cracked. So you need to make sure that at the location of the link slab, you have to debond your barrier. So when you design your barrier for the crash loading, impact loading, you need to take that one into account. They all link together. Even in the design and detail, it's all linked together. And then the detail all elements in bridge to accommodate bridge movement. Yeah, like you see those small detail, they are important. These are small detail important, right? And yeah, as I mentioned before, that at the link slab location, you can see this detail 170 meter wide bitumen paper over the pier to debond the zone. You can see that that dimension, the debonding length is 1650. We put 1.7 meter in length to debond that one. You can see these things are very important. And the bridge bearing plinth and the hog calculation, that's very important. Unfortunately, I don't have a time to go through this one in detail. And the geometry of the hogging need to be, you need to take into account. This is very, very important. And provide the upstand for strip seal and expansion joint to prevent leakage. These are the simple thing. You need to make sure that is good enough to make sure that properly construct and then is properly performed. Check performance of bearing during seismic event like this. Detailing is very important. The mine subsidence effect, this is something you build in the mine subsidence areas. Like if you build something in Ratnapur areas, the mine subsidence effect, that is the totally different area. The bridge design exactly same, but you need to design the bridge to accommodate that loading. And then if the bridge is underwater, you can see, we saw a lot of pictures thing. If a bridge is going to go up, you saw the last time the calculation, the uplift, they are quite significantly large. Then you need to provide the vertical restraint. But please remember that if you provide restraint on the bridge, your bridge is moving in the longitudinal direction. You need to make sure that your restraint have a slotted hole in your plate to go in the longitudinal direction. Okay, your restraint is always moving in and out, but vertically it can hold the bridge. These are the simple thing. As a designer, the way you can build, you can just draw a piece, get a piece of paper, draw a block, restrain, vertically fix, and laterally move. Just draw the arrow, laterally move. I need the slotted hole, vertically fix. I just, if you put the plate on horizontal way, vertically please, I have a nut and a bowl to move that one. Normally we use Teflon as a washer, use the Teflon washer and tie. And if you have that detail, this will move in and out. These are the very simple thing. You need to learn and you need to apply. Please go and spend some time regarding Teflon. Yeah, just spend some time, read about Teflon, and that's a very important material. Yeah, friction is near zero. And then the elements, if not accessible, you need to design for 100-year design life. In Australia, when we design the bridges, wherever we use like this double joint, for example, in this location, we always use the stainless steel. So because the stainless steel, so we guarantee 100-year design life. Drainage and expansion joints, they are very important. Yeah. Normally, when you use the joints, if it is the if you got a shared user path, or you let the people to ride bicycle or anything, because the bicycle tires are small, you can't have not like a car tire is quite wide, so you can car tire can like 85 millimeter gap, it can pass over, but the the cycle can't, because to prevent that risk or hazard, you have to put the plate on the top. Please make sure that that plate need to be detailed, fixed one side, free on the other side, is move on top of each other. These are the minor things, just a sketch, think and sketch and see, then you will see how to fix it. These are very important, and they provide safe access for maintenance. So you need to inspect your bridge, you need to inspect your bearing, you need to have access to them, you need to provide safe access. You need to see whether people can get there or not. You can bring your machine there or not. So this, because if you want to replace your bearing, everything you are bringing there is very heavy. So therefore you need to use machineries, you need to make sure that you provided that one. Yeah, quickly if I touch base with this one, this the figure 1, the drainage at the expansion joint. You can see this, the expansion joint is allow. I said you can allow the movement up to 200-300 millimeter. You have a significant gap in here. It's depend on the length of the bridge, the thermal, expansion. This bridge, this particular detail I pick. The length of the bridge on the either side is more than 220 meters. Because of that, there's a significant expansion of the bridge. When the bridge is expand, the gap will reduce here, the gap like a contraction, because you have a reasonable gap. Then you have a big gap in here. When it's rain, the water will go down. To capture that water in here, you can see this slide very closely. Later, we have a flash in here. We collect that water. That water will be go through a gutter. From that gutter, we collect it from a down pipe. That down pipe, it collected to a hopper, and from that hopper, we just drain out. So to the be connected to the pipe. This is one detail. And the other detail I just put in here. This is I don't have much time to explain this one. In the next presentation, I will spend some time. You go back and read about, because when you as I mentioned in my second the slide, when you apply the post tension in the pre-stressed concrete girders, there will be a significantly large hook. Because of this hook, when you are placing the bearing on top of when you place the super T girder, it looks it's flat, but actually it's not. Because of that, we create what we call the epoxy mortar block. We create some people, we grout that one. But in here, we just create the epoxy pre-molded box, and we attach that one. This detail, and then the reason we need this element in here in the design, we assume the bridge bearing is truly horizontal after we construct. We place and deflect, it will be fully horizontal. You can test that one using A4 paper concept, as I mentioned before, and then we use this concept. Because of that, remember in the bearing design, I say the rotation, the axis of parallelism, because if they are not parallel, there is a rotation in this bridge that's going to affect significantly in the bearing, elastomeric bearing design. Because elastomeric bearing design, the maximum rotation we allow is 1.5% radians or 15 milliradians. If you have a construction tolerance itself is the 0.5% radian, that will absorb a lot of design element into that one. You need to have a larger bearing. That is the reason. That is very important in the design detailing to understand that. In this one, we spend a lot of time, a lot of calculations to calculate the girder camber, to give the contractors the variable numbers. We calculate the camber over the different period of time, different values. Then we calculate these dimensions for the various cambers. And then in between, the contractors can interpolate according to, I mentioned this one before, they can measure this camber out quite easy. Wherever the place you go to a hardware shop, you can buy a laser, you can measure any deflection now. Not back when I was young and go to check this stuff in the site, but they are quite quick and fast nowadays. Because of that, you can check this camber, then you can select, you can develop your epoxy mortar box. We use high strength concrete and things to get this thing working get the strength right very quickly. This thing we need to detail. This is the one of the important part. I will put some information in the reference documents. Just go and study. I think this is the end of the presentation. We don't have much time. You can ask the questions. We almost past 4 hours now. The important thing I just want to mention to you, the next session by Professor Penan Vanichai is a one in a lifetime for you to listen to a person like his caliber about a structural dynamics. It's a lot he will share with you. This presentation will be exactly 2 hours because it's on a Friday. It's in Bangkok between 1 o'clock, sorry, 1:30 to 12 p.m. in Colombo, in 5:30 in Sydney, and I think it's 1:30 in Bangkok, 1:30 to 3:30. Because of that, the whole presentation will be 2 hours. The professor will send me the topic what he's going to discuss, but I already informed the audience and the intent of this presentation, because I just want to give you guys the earthquake engineering and wind engineering background and how we're going to apply that one in the bridge design. He might discuss with you sometime the very special example in cable stay bridges or something. But anyway, he has been teaching in AIT, doing research for masters and PhD student more than 30 years. So it's a once in a lifetime opportunity for you to listen to a person of that caliber. Please share this one with your friends. And because the CSEC, they were kind enough to host this one, and then the YouTube channel, a lot of people can log in and can listen the presentation live. And because of that, you can share with your friends. So the please tell me if you have any question, 1 or 2 questions, I'm happy to answer. No questions? So then if there's no questions, then I will be there in the next big presentation as well. So then if there's no question, see you in next week with the Professor Penan presentation. And then we're going to discuss on the week after, that means 26th of November, we're going to discuss about the bridge modeling. So after this, if you understand all this section, if you know how to model the bridge element, there are not many elements in the bridge, you should be able to model and design a bridge, because design is the bridge or a building or any concrete or steel element is exactly the same. Yeah, the fundamental exactly the same, the way you design the same. Yeah. If there's no questions, so then I would like to thank again Chatumi and Dilina and CSEC for organizing this presentation. Thank you very much for attending. And yeah, thank you so much. Have a good night and a good weekend. Yeah, thank you.